Good morning, Astronomy 1010. Welcome to Lecture 3, Part 2, where we will recount the history of astronomy in a highly compressed form. And then we will do our third homework, which follows Chapter 3 from the book, the history of astronomy. Last time I told us that we were going to do a couple of little tidbits on planetary periods and timekeeping, but I decided today that I was going to integrate that into the history lesson rather than start off that way. I think that'll be better for us come homework time. So helping you or teaching you guys a little bit about the history of astronomy not only preserves that tradition, but it helps you to understand why astronomers think the way they do and what sorts of things they are looking for. And what motivates them to study stars and planets and why it's helpful and useful. Keep in mind that if you've started to get the idea from our lectures so far, the nighttime sky is a giant clock, and it's also a giant calendar, a natural clock and a natural calendar. During the course of a single night, or even a single day, the rotation of Earth gives us what we would call the diurnal motions of the sun, moon, and stars, meaning the sun rises in the east and west. That's a natural clock. The stars rise in the east and west at night, and they are a type of clock. There's a sidereal clock and a solar clock. And the passage of time throughout the year as the sun drifts along its ecliptic, that is a calendar. On our celestial globe that we used last week, we actually moved the sun to different dates along the ecliptic, and the ecliptic path can be thought of as a sort of calendar that the sun is traveling along. There's also planets, and we've talked about, I believe, the number of planets visible to the naked eye. Have we not? How many planets are visible to the naked eye? Cole says 5, and he's correct.
Oh.
And for those of you who might have missed the lecture, those 5 planets are Mercury, Venus, Mars, Jupiter, and Saturn. And maybe a nice place to start is just a quick useful note, which is something like this. How do I know it's a planet when I see a bright, shiny dot in the sky that for all intents and purposes looks like a star? So there's a couple of things. First of all, planets are brighter than stars. So oftentimes, if I'm, going about my day-to-day business and I run into someone who knows that I'm an astronomer, they'll say to me, hey, I saw this thing in the sky last night. It was this really bright, shiny. I'm just like, Venus. I mean, usually I'll say, what time of night was it? Where in the sky was it? Was it in the east or the west? But 9 times out of 10, if I just say, oh yeah, that was Venus, I'll probably be right. And the second answer would be Jupiter, right? So the stars Venus and Jupiter are the brightest planets, followed by Mars and Saturn. And even Mars and Saturn are much brighter than even the brightest star, Sirius. Mercury's a wee bit tricky because to see Mercury, you only see it for a tiny little bit just after dusk or just before dawn. And it never really gets far above the horizon. So unless you've spent a lot of time on a ship at sea or on a tall mountaintop or in a very dark sky with a flat desert plain, you probably have not seen Mercury very often or even at all in your life. Planets are brighter, so that's one thing. But even though they're brighter, they are still essentially point sources. When you look at a bright planet, the experience is similar to looking at a star. It's a bright dot on the sky. And just the fact that the planets are brighter would not have been enough to tell ancient people that they were different than stars. A second rule of thumb that's very useful is stars twinkle, but planets don't. the light from planets is much steadier than the light from stars. And that has to do with their angular size. The typical angular size, I think I have that screenshot. Actually, I want to grab the 1020 lecture because that has a couple of good pictures that I don't have here. Come on, baby. Here, let's get out of this for a second and let's go. Sorry. Here we go. Angles. Here we go. If you remember this slide, when we learned about the angular size of, well, when we learned about different units of angle, I should have taught you about arc minutes and arc seconds. An arc minute is 1/60th of a degree, or the equivalent of seeing a soccer ball from half a mile away. Jupiter and Venus both have an angular size of roughly 1 minute of arc. But stars like the supergiant star Betelgeuse, they have angular sizes of 0.05 arc seconds. And arc seconds are much tinier angles than arc minutes.
What?
They're 1/60th. Someone's got.
What happened?
Hey guys, hold on. Someone forgot to mute themselves, and I can hear you talking to your kid brother or something. So let's see here. Now I've got to find you, and I'm going to shame you, Nina. Nina, who forgot to mute. And what the hell happened, Nina? I'll tell you what the hell happened. You forgot to mute. Okay, so don't forget to do that, or I will make fun of you. Okay, so let's hide the trolls again. There we go. Okay. Anyways. So the fact that a planet has an angular size of 1 minute of arc means the beam of light from a planet is much steadier and cannot get pushed around by the molecular motions of our atmosphere. The twinkling of stars is caused by the fact that the air that we breathe and the atmosphere of our planet is a sort of fluid. And if your starlight is a hyper thin pencil-like beam, even molecular motions can cause that beam to dance around in the sky. Even if stars twinkle and planets don't, that would not have been enough to tell an ancient observer of the sky that planets were fundamentally different than the twinkly lights that are stars. The real thing, the important thing, is that unlike stars, planets wander. Planets wander against the background stars. And that makes them more like the sun and the moon than it does like stars. In fact, the Greek word planetos, which I cannot spell in Greek, sorry. Planetos is Greek for the wanderer. If we haven't talked too much about the wandering of the planets, it'd be a good idea to show you guys a little slide on how that works. So somewhere down here, yeah. Oh, by the way, if I haven't mentioned this, it's a cute little fun fact that is worth mentioning. Our 7-day-a-week calendar is based on the 5 naked eye planets plus the sun plus the moon. Those are the astronomical objects which are not stars in our sky. So the sun is for Sunday and the moon is for Moon Day. And the names of the other days of the week are brought to us because English is a mixture of Germanic and Latin languages. And there was a mixing of sort of Nordic Viking culture and Latin culture throughout the years that mixed up the gods, right? So Jupiter, for instance, you know, the king of the Roman gods, got mixed up with the German god Thor, and that gave us Thor's Day, right? And Mercury was associated with the fleet-footed messenger god Woden, the trickster wanderer, and that gave us Woden.
Is this a joke? Is it real?
Oh yeah, no, this is totally real. So if you don't like Mondays, as the Town Rats say, you can blame the moon. Okay, like of course it's real. Every single aspect of your daily clock, timekeeping and calendars are all about the motion of astronomical objects through your sky. The sky is a clock. It's a natural clock. 7 days a week are related to these naked eye astronomical objects. Months are based on the orbital period of the moon, in particular the synodic period of the moon. And the number of days in a year are related to the journey of the sun against the background stars, right? So let's see what it would look like, because obviously we don't spend night after night staring at the sky anymore. We've got better things to do, like Nintendo or something, okay? And ancient peoples didn't have such distractions, so their Nintendo was the nighttime sky. That was TV, that was mythology, and that was religion, all baked into one free show. So if you go out at night in the summertime and you look towards the south, you can see the constellation Sagittarius by a grouping of stars that are a bit brighter than the others, and they're called the teapot. The teapot is what is called an asterism. It's a grouping of stars that's not a real constellation, but it's almost like a real constellation because you can see it so clearly. For instance, the Big Dipper is an asterism, but it's really part of the constellation Ursa Major, the Big Bear. So in Sagittarius, there's this grouping of stars called the teapot. And you can't see the teapot on every day of the year. You could not see it tonight, for instance, but I have seen it when I was looking south. In particular, one night I remember being at the ocean mist and crawling through a little hole in the fence and sitting on the beach there after I left and looking south towards the horizon and seeing the teapot. And it looks just like this. The teapot can be seen during the summertime, and then as the nighttime sky drifts throughout the year, you won't see it anymore. But when you do see the teapot rises in the east and it sets in the west, and all of the stars in the teapot maintain the same relationship with respect to each other, okay? And that's key. On the other hand, if you were to see Mars at night near the teapot, the whole situation would probably go like this. One night you sit down on the beach and you see this little red star, or this bright red star, and you think, oh, that's interesting. There is a bright red star and it's somewhere near the spout of the teapot. Isn't that cute? And if you forget about it and then you come back 2 nights later and you sit at the same spot on the beach at roughly the same time, you'll see Mars again. But this time Mars will be over here after 2 days, and you'll say, you know, that was kind of weird. I could have sworn the top or the spout of the teapot was perfectly lined up. It almost seems like, no, I'm crazy. That can't be happening. And then you go out 2 nights after that, and sure enough, you think, okay, no, this is really happening. That star was not where it was the night before, and now it's closer to the top of the teapot. And if you were an ancient observer of the sky who didn't really know what was going on here, if you hadn't been trained in the Copernican solar system, you'd be thinking, that's a little crazy. It's crazy that of all of the tens of thousands of stars I can see in the sky, the 5 brightest ones don't maintain a fixed position, but night after night, they appear to drift. And the drifting night after night is eastward along the ecliptic. You know what else drifts eastward along the ecliptic night after night? The sun, the moon, and they also traverse the same plane. They are traveling through those zodiac constellations, Sagittarius and Taurus and Cancer, because that's the disk of our solar system, right? What really messed up ancient people was not just that these planets had a constant eastward drift. That already made them kind of more like the sun and the moon than like other stars. But the thing that was unique about planetary motions is at key times in the year, planets exhibit something called retrograde motion. And for a few nights in a row, Mars will stop drifting as far along the ecliptic as you're used to seeing it. It almost seems to hover for a week or so in the same position. And then, crazily enough, the planets will begin drifting westward along the ecliptic. And this is something called retrograde motion. All planets go through it. And it took Nicholas Copernicus to explain to us why this happens here. Nicholas Copernicus didn't explain this until 1500s, and even when he did, not everybody believed him. Up until that time, people searched in vain for reasons to understand this very kooky and complex motion. As far as Greeks and Romans were concerned, they practically worshipped these dots in the sky as their gods, right? Their god wasn't an abstract old man who got mad when you said swear words, who you never see and never hear. Their god was a very tangible thing. You could look up on the sky and see Jupiter making his way through the heavens, right? So to understand the motions of the planets then was more than just science or astronomy. It was understanding the minds of the gods, right? Let's take a quick note of this, or about this. Planets undergo something called retrograde motion. And a quick and dirty definition of retrograde motion could be something like a temporary westward drift along the ecliptic made by planets during the year. There's probably a better definition, but this is sort of how I think about it, okay? And if you want another fancy vocab phrase, when planets do this thing here, historically it's referred to as a retrograde loop. The desire to understand the retrograde loop is actually the origin, not just of the science of astronomy, but even the history of physics and mathematics is bound up in this. Greek geometry in the development of mathematics was constantly being pushed forward by astronomers who were trying to understand the machinery of the cosmos. And that's kind of a cool thought, actually. Astronomy is like, it's even older than math, which is wild.
That's true. I think, who was it? Pythagoras? Like Pythagoras theorem. He believed like the universe was like the center of it all.
Well,
and stuff
you probably
like,
mean you mean the Earth was the center of it all, right?
Yeah, the center of it all. Something like that. I forgot how it went.
And so let's bring us round to this here. You know, if you want to really get into the history of astronomy, and I had a very lovely class when I was in college, which was it was an entire course dedicated to the history of astronomy. And it was kind of like a half astronomy, half philosophy course. It was so super cool. And when you have that much time to spend on this subject, you realize that it's a beautiful and a very cool and rich subject. We don't have that much time. I'm going to compress it into a 1.5 hour lecture today, and I'm probably going to do it badly. Okay. But you can start looking back to things like Egyptian astronomy, Babylonian astronomy, the sort of development of astronomy across all kinds of different cultures, right? Like you can find these structures around Earth that are not simply sort of like religious ritual sites, but they're also astronomical clocks. A cool example is Stonehenge, right? Stonehenge has this kind of cool history of being developed by these British Druids or something, some prehistorical society that predated the Roman invasion of England. And the thing had been sitting around for so long that most people thought that the Romans built it until they discovered a Roman centurion's journal or some kind of a Roman general's journal in which he talked about conquering England in some, war campaign and discovering this structure there and said, wow, I can't believe these crazy savage Druids built this amazing monumental structure, and they were performing some human sacrifices in it, and it was kind of wild, right? And at first people thought, okay, this must have been a religious temple. But over time, archaeologists who also understood some things about astronomy realized that if they wound the clock back to the time when these structures were built, the positions of the sunrise and sunset had been different than they were today because of the precession of Earth's axis tilt. And if they discovered the positions of the stars when these structures were built, that the sunrise, the rising of the sun during the summer solstice, aligned with the sort of primary heel stone. So these were kind of guide markers for where the sun was going to be rising at key times of the year. And when you realize that, you suddenly think of this whole thing as a sort of clock or like a sundial or a calendar that these people were using to keep track of the motions of the sun. And also probably alignments coincided with moon rises and possibly even the planets. In the Aztec city of Tenochtitlan, which is where modern day Mexico City is, Templo Mayor was designed so that these twin pyramids would bracket the sun on the day of the spring equinox. So on the day of the spring equinox, the sun would rise right through the center of these two temples. And I bet it shined a big shaft of sunlight, kind of Indiana Jones style, down at the center of this courtyard. And the meaning of that beam of light would have been clear to all of the people who were part of this society. It would have been, get up, get out into the fields and start planting some corn or something, right? This would have been a message that it was time to get to work. And so these calendar clocks were very important because agricultural people depended upon them to know when the planting cycles were taking place. And your entire city could live or die depending on you executing that properly. There are all kinds of cool structures, like Chichen Itza was dedicated to different positions of the planet Venus, and there are slots carved into these temples, pyramids here that align with Venus at certain times of its planetary cycle. So there's so much to study about ancient astronomy, and we can't really do it all or even any of it, honestly. What we are going to do is we're going to give you a little whirlwind blast through a few key astronomers in the history of Greek astronomy, because Greek astronomy developed in a way that's a little more similar to how we work in modern science. And some of the Greek approaches to astronomy were different than other ancient societies. In particular, because the Greeks were the first recorded people to try to explain observations of the natural world in terms of other natural world phenomena, okay? So in the history of Greek astronomy, it is said that Thales of Miletos, this Ionian philosopher, was supposedly the first person who is known to have recorded down or written down what we consider to be an early primary science question, or he was one of the first people who developed a sort of call and response that sounds like modern science. He writes, what is the basis of nature and its variety? Where do we get all this stuff, the planets and the stars and the mountains and the rivers? His answer was, everything is made out of water. And this is considered the first time in human history that someone tried to explain something in nature, in the natural observable world, in terms of another natural substance like water, which everyone can observe. And that's different than an anthropomorphization of your cosmos, right? Instead of this, it could go, well, why did the thunderbolt strike my house? And it could be, well, Zeus Poseidon was angry at me because I ate too many chickens at the relay race, and that, I had to be punished. And that is a telling of phenomena in the natural world based on some sort of mythological story. It's not something that can be easily observed by other people. So goofy though it may be, this is considered to be one of the first scientific questions and answers. And what's interesting is, as soon as Thales presented everything is made out of water, I should mention that he was an Ionian philosopher. He lived on a set of islands off the coast of Greece. So if you grow up surrounded by water, maybe that's a logical explanation. But unlike other cultures which believed in a sort of flat earth with, turtles all the way down, and it's funny how the flat earthers work here. There's always a definite direction of goodness. Good is in the direction of up, and anything down is not so good. But the Greeks actually had been teaching their students that Earth was a sphere and it was floating in empty space. And Anaximander taught his students that up and down were relative, and he sort of developed that celestial sphere the one that we used for our lectures even today, right? So we can trace this model of the cosmos here right back to Anaximander. Also interesting to note that Anaximander argued with Thales about the nature of everything. He argued that everything is not made of water, but in fact, everything is made of fire, some sort of primary fire. I'm not sure if the celestial sphere were like little holes with the primary fire hidden behind it or something like that. But do you see what's happening? If someone says, I think everything is made out of water, and then another person comes along and says, no, that's preposterous, everything's made out of fire, then you've already begun the process of science, because now people are arguing with each other over which theory of the universe is correct. And that sort of sounds very much like modern science to me. It's measurement and then it's argument, okay? And you're trying to convince each other that your hypothesis is correct. Someone mentioned Pythagoras. Thank you for that contribution. Pythagoras was important in the development of astronomy. We lost many of the works of the ancient Greek philosophers because most of them burned down in this temple in Alexandria by some religious zealots who set this library of Alexandria on fire, and we lost all these papyrus scrolls. But other Greek writers who did survive have little reference notes to the writers who came before them. And I believe Aristotle mentions that Pythagoras had taught his students that Earth was a sphere. And Aristotle picked up on that and continued to argue for a spherical Earth. I don't know if I mentioned this in our last class. I think I said it briefly, but just in case you forgot, one of Aristotle's arguments for why the Earth was spherical, he mentions partial lunar eclipses. And he says, that's Earth that's casting the shadow on the moon there. And if you look at the shadow of Earth projected onto the moon, you can see that Earth is curved. That's one reason why you would know Earth is a sphere. And I guess since people have started to ask me now about flat earthers, that's actually, at first I thought it was a joke, but supposedly there are people who aren't down with this ball Earth hypothesis, you know. But something to think about with a flat Earth versus a spherical Earth is this. Let's say that your local sky looks like this. We kind of drew this picture in our previous classes. And you remember that a big deal for our class was that we learned that the altitude of Polaris is equal to your latitude on Earth, right? And that means the height of Polaris in your sky will change as you walk from the North Pole down to the equator. At the North Pole, 90 degrees, Polaris will be at your zenith. At the equator, Polaris will be on your northern horizon. If you lived on a flat Earth, wherever the sky would be really infinitely big, and wherever you walked around on that flat Earth, Polaris would basically have roughly the same angle in the sky. It would not change its position. So the Greeks knew that if you take a ship north or south and you can see the angular positions of stars changing, that in itself has to prove that you are on a curved surface and not on a flat surface. So never forget that argument when your flat Earth friends start trying to argue with you at a bar, okay? In fact, they probably aren't going to be able to understand that, sadly, but hey, I did a thing, and I'm a little embarrassed here. There's the view, gallery. Okay, good, okay. I was having trouble getting back to this gallery view so I could see all your faces. There are many Greeks that we could study, and when I took this course, I had to memorize a long list of them. We're going to focus on 3, just to keep things simple and to get the flavor of the feeling. And one thing that I want to share with you guys before we take notes on those 3 Greek philosophers who had the strongest contribution to Greek conception of astronomy is I'd like to show you what the Greek solar system looks like for all 3 of these philosophers. It was something like this. First and foremost, the Greeks subscribed to a geocentric theory of the cosmos. Geo meaning Earth and centric meaning center. They believed that Earth was the center of the entire cosmos and that everything, the moon, the sun, the planets, and the stars, all revolved around Earth. And as you know, that is not an unreasonable thing to assume, because that's what it feels like. It feels like when you walk around outside that you are on a flat, stationary, okay, they were sophisticated enough to know that it was a sphere, not a disk, but they still believed that the Earth was not moving and it was the center of everything. That's one thing, but notice, guys, if you look at the orbits of the various astronomical objects, they basically correctly deduced the relative positions of the planets. The moon is closest to Earth, and that is true. And the order of the planets does go Mercury, Venus, here they have the sun, Mars, Jupiter, Saturn. The sun was another orbiting body, and the stars were all fixed to that background celestial sphere that Anaximander had described. This might be an unfair question to ask, but how did they do that? I mean, just think about it yourself, right? You're out there at night, you're looking at planets, you watch them wander or drift around with respect to the ecliptic. How would you know that Mercury was before Venus, that Venus was closer than Mars? Matteo, talk to me.
So I don't know if I'm right, but isn't Mercury, Venus, and then Earth? So if they thought the Earth was the center, wouldn't Venus come before Mercury? Because it's closer to Earth?
That is a great question. Yes. And I actually at one point had that confusion, or not, it's a good question. I wondered the same exact thing. If it was just based on distance, why wouldn't, perfect question, Matteo, why wouldn't Venus come first? Because Venus is closer to Earth. I think the answer to our question is the way in which they measured those distances was based on the orbital period of the planets, by which I mean, well, which you think I mean time to go around the sun, but there are two types of planetary period. And we had this thing in our homework, and this was one of the things I wanted to start with today. So I figured right now would be a perfect time to kind of reintegrate it into our lectures. Okay, if you were in a flying saucer and you were hovering above the solar system, it would be relatively simple to observe the orbital periods of the planets because you would just kind of watch them go around the sun and you would keep track of that motion. But now remember that you are on a ball on an Earth that is also orbiting the sun, and that makes things more confusing. There are two types of period. There is a synodic period and a sidereal period. So here, once again, is the sun, Earth, and Mars, and they are in alignment. And there's all these cool old-fashioned astronomy terms for alignments that the planets make with the sun. I have a picture of some old-timey time astronomy here. Okay, in this diagram, let me walk you through this. The sun is the yellow ball. This is an inner planet like Venus. This is Earth. Do you guys see that symbol with a circle and a cross in it? That's the astrological symbol for Earth. And you're actually going to see me use that throughout the year. This is an exterior planet to Earth's orbit, like, for instance, Mars. When Mars is in a configuration where it's opposite the sun, we call that opposition. And if you were a person in ancient Greece observing Mars, weirdly enough, even though you might not have known that Mars and Earth were going around the sun, you would know when Mars is in opposition, because in opposition, Mars has the same geometrical alignment as what phase of the moon? Here's a test question. When Mars is in opposition, it should have the same relationship to Earth as what phase of the moon? Who knows their lunar phases? Look at your little note that we made last time. Cheat.
New.
Not new.
Full.
Full.
Over the AM.
Full moon. Ethan,
Oh,
your
yeah.
new would have been correct if you were talking about Venus in inferior conjunction. But in opposition, Mars would have the same configuration or position relative to Earth as the full moon. Now, we know some things about the full moon from our last lecture, right? Remember how we tried to figure out the rising and setting times? We imagined an observer whose meridian was pointing in different directions, right? And then we drew in their horizon line at a 90-degree angle. What time would Mars rise when it's in opposition? What time would Mars set when it's in opposition? What time would Mars cross your meridian in opposition? These are questions you should be able to answer if you think about it carefully. Can anyone do it? How would you even know the answer to that? Let's give you a hint. I mean, I can tell you the answer, but I think it'd be so cool if you guys could figure it out. What time would Mars rise when it is in opposition? Shoot, sorry, 83. So let's see.
Midnight?
Midnight is the answer to which question?
I'm assuming the meridian one? When
Yeah, because when your meridian is at midnight, that's when you're pointing most directly towards the full moon. Or in other words, in your local sky, here, let's go back quickly to my board, right? At midnight, so the motion of the moon is going to be to rise in the east, right? It will come up and cross your meridian at midnight, and it will set in the west. So if the full moon crosses your meridian at midnight, then what time would it rise and what time would it set? We did this last time, and several of you were able to answer these questions last time.
It would rise at 6 p.m. and set at 6 a.m.
Correct. That's right. Because remember, your horizon is a line that goes right through the center of Earth. When your meridian is pointing towards 6 a.m., your horizon line is like this. It cuts through the center of Earth. And that means your local sky, this is all your local sky, right? So at 6 p.m., there's the full moon rising in the east, right? Sorry, yeah, there's the full moon rising in the east. Sorry, the arrow represents the direction of the moon in your local sky. Your horizon is actually moving in that direction, right? That's why this gets so confusing. So it rises in the east at 6 p.m. It'll cross your meridian at midnight. And then when your head is pointing in this direction, your horizon will be like so, and that's when the moon will set in the west. Okay, so the full moon is up all night. That's how we remember it, right? Now, transport yourself over to Mars for a second, or transport yourself into the mind of a pig farmer in ancient Rome who's observing Mars. Not only would opposition be a special day, because Mars would cross your meridian at midnight and it would rise at dusk and it would set at dawn, but do you see how much closer Earth is to Mars in opposition? That means Mars would be really, really bright in your sky. You'd be watching Mars get brighter and brighter and brighter. And at the apex of its red brightness, at that moment, it would cross the meridian at midnight and be up for the entire night. That would be a special day. That would probably be time to wage war on your enemies because the Martian god was at its apex of strength or something. You know, this is probably how the whole thing went. Time to unleash the chaos. So these are moments when people would have been paying attention. Okay. In that case, imagine watching Mars night after night, getting ready for that key moment when it was time to deliver bloodthirsty war against the Persians. One night, you see Mars is in opposition and you get really excited and you think, all right, time to kick some ass, all right? And then you go and wage your bloody campaign. Maybe it works, maybe it doesn't. And then you wait a while. A year later, Earth has gone around the sun, But Mars takes longer to go around the sun. Its period is about 2 years. So during 1 year, Mars has traveled over here in outer space, and then Earth starts to catch up to Mars. And in about 1.5 years, suddenly you're back to opposition again. The sun, Earth, and Mars are all in alignment. They're all in a syzygy, a 3-body alignment. And if you're the pig farmer or you're the Roman centurion standing in a field, it looks like Mars is back to the original position because it's back in opposition, and it rises at dusk and it sets at dawn. But Mars hasn't actually gone around the sun. It's just that its Earth is caught up to it in its orbit. And that's where we get our 2 types of planetary period. Bear with me here because I'm trying to do a couple of things at once. Let's take those notes just to have them. Okay, so here's the question. The question is, how did Greeks know the approximate order of the planets? And this is also, I can't remember who asked it. I think it was Matteo. Matteo, this is the same answer to your question of how they believed Mercury was closer than Venus. The answer is by observing their synodic periods. And this is a great opportunity for us to review the difference between synodic and sidereal period. So first of all, when we do homework problems or when we do test questions, the sidereal period is called P-Sid. And the sidereal period is the normal, how long does it take to go around the sun period. So it's a true 360-degree orbit around the sun. That's what you're interested in a physics sense, okay? I was going to say, oh yeah. In case I didn't mention this, the word sidereal means with respect to the stars. So if the stars are so far away that they constitute a sort of background reference frame, it's how long does it take to orbit the sun relative to the background stars. On the other hand, P-Syn, S-Y-N, is the synodic period. The synodic period, if you want to put it really succinctly, really short definition, it's the time between oppositions, where I'm using a key vocab term, opposition. And if you want to stretch it out a little bit longer, you could say in a loosey-goosey way, it's the time for a planet to orbit around the sky or something like that. It's the time to get back to a configuration where Mars is crossing your meridian at midnight. There's a relationship between these two things. The important thing to remember is that the synodic period is the observable. Unless you're in a flying saucer, you cannot directly observe the sidereal period. You observe the synodic period, and then you calculate the sidereal period. And there are 2 formulas depending on whether the planet is interior to Earth or exterior to Earth. So for instance, for inner planets like Mercury and Venus, and I mean inner to Earth in this case, the sidereal period is the synodic period divided by the synodic period plus 1 year. For outer planets, anything outer to Earth, Mars, Jupiter, and Saturn, and all the way out to Pluto, really. Then you have the sidereal period is the synodic period over the synodic period minus 1 year. And if you guys remember, last week we did this for a homework problem. So you could go back and review that video, and I show you how to punch it into your calculator using parentheses. It's not very hard. So the only difference in the formula is whether there's a plus or a minus at that position there. Okay, now I'd like you to think about this one step further. The synodic periods will change depending on how far away from Earth you are. And what I'd like to do here is use a whiteboard and have you think about the difference between something like Mars and something like Pluto when it comes to a synodic period. So first, let's put the sun at the, let's pretend we're Copernican for a second. We'll put the sun at the center of the cosmos. And now I'll represent the orbit of Earth like so. And now I'll represent the orbit of Mars like so. And I'll use black to represent the orbit of Pluto, which is much, 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 much further away. Okay, so some basic facts. It takes Earth 1 year to go around the sun. Okay. So here's Earth, 1 year to go around the sun. It takes Mars 2 years to go around the sun. But Pluto, it takes Pluto 250 years to go around the sun. A Plutonian year is 250 years, right? So let's walk our mind through what would happen if we were observing both Mars and Pluto in our sky. In 1 year, Earth would go around the sun, and Mars would have gone maybe halfway. Mars would have gone halfway through its journey, right? Because it's got a 2 year period. But in 1 year, how far would Pluto have gone? It would have gone roughly 1/250th of its orbit, right? So Pluto in 1 year only does this, but doop. In other words, Pluto basically doesn't move very much in the course of 1 year. So weirdly, the farther away, this is the real answer to your question, Matteo. So get ready for it, because I had to build this up. The farther away from Earth you are, the closer your synodic period is to 1 year. Because in 1 year, you loop around the sun and Pluto is back in opposition, right? Okay, 1 year plus a little bit, 250th, right? But for Mars, you actually have to wait 2 years to get back into alignment. Isn't that weird? The closer the planet is to Earth, the less often you go into opposition in your sky. And I suspect that, okay, my mouse is freaking out on me, guys. All right, let's clear drawings. And let's exit.
I mean, that makes sense, because if the planet is farther away from you, like, it doesn't really move. So
Yes, that's what I was trying to say. And forgive me but all of this was part of the lessons, right? And I think the real message here too is something even different, which is the Greeks were sophisticated observers of the nighttime sky. They knew their geometry very well. It is said that when Plato developed the first lyceums, the schools on which our modern day university is based off of, because a cool thing to do in ancient Greece was young men would get together to have an intellectual discussion, and eventually that kind of gave birth to these lyceums or schools, and they eventually evolved into modern day universities. Plato carved in the wall of his first lyceum, "Let no one unversed in geometry enter these halls." If you know, geometry was the heavy metal of ancient Greece. If you didn't know that, you weren't cool. You weren't a cool dude to be hung out with, right? So these people were sophisticated observers and sophisticated studiers of the nighttime sky. We would like to focus on 3 Greek astronomers today. And let me just check the time, because I cannot be doing well. I can, 2:30, yeah, I'm screwed. Okay. Let's get down to our 3 Greek astronomers. And now that we're in the right feeling of things, I'm going to erase this. Okay. So Greek astronomy was fundamentally a geocentric view of the cosmos. And geocentric, of course, means Earth-centered. And although many different philosopher astronomers contributed to this geocentric model of the cosmos, three in particular had very important roles to play. And they are Plato, the famous philosopher who you've probably heard about, Aristotle, another famous Greek philosopher who was the student of Plato, and then a Greek that an Arab Greek astronomer you may not know about called Ptolemy. And this is not the Ptolemy that's the brother of Cleopatra. That's something else. Although, you know, the ancient world was all connected in some way, but this is the Greek mathematician, or the Greek Arabic mathematician Ptolemy of Samos. And I can direct you to a Wikipedia page if you're interested. Okay. These three philosophers came at different points in time, and they fundamentally contributed to Greek geocentrism. Plato is probably the most abstract, so let's start there. And let's see if I can grab a slide or two, have some dates and some things to think about. So the contributions that Plato made were to the way that people thought about the cosmos for literally thousands of years afterwards, because Plato is a very cool and easy to read philosopher and very witty. And I encourage you, if you ever get the chance to take a philosophy class where you get to read Plato's Republic, it's a fun and interesting book. It's not boring. Plato believed that the heavens were timeless, unchanging, eternal, and immutable. And this was a very important concept in Greek science or in Greek philosophy, that the world of Earth, where we had our earth and wind and water and fire, the primeval elements, that world was a mutating, changeable, corruptible, deteriorating, transient place. But that the heavens had perfect cyclic reproducibility. Like when I told you guys about the teapot in Sagittarius showing up in summertime, they believed that the heavens were this perfectly synchronized clock, and that the materials of the heavens were a magical place that was not like Earth. So Plato believed in a timeless, unchanging cosmos. The word is immutable. Immutable, never changing, okay? Plato also believed that the planets were perfect formless spheres.
Could you show your work again?
Sorry, am I not doing something right? Were you talking to me?
Whatever your terminology was for that third definition you don't have. Well, the second, apologies, whichever one you just erased.
Oh,
I
that
didn't
was
get notes
that
on
was
that.
Aristotle.
Oh, okay, okay.
And I will be.
I hadn't understood why it got erased so quick. I was still trying to catch up.
I'm sorry, and I usually ask. So I think what I was planning on doing, I don't know if that's Preston or someone, but I was writing down the three Greek astronomers, Plato, Aristotle, and Ptolemy. And then I started to realize I did not have enough room to write all the Plato stuff in. So since I'm going to get to Aristotle next, hopefully that'll be okay. In fact, Preston, do you mind if I erase this one too? Because I'm going to write him down again in a moment.
If you're ready to catch up.
Yeah, okay. So Plato, we'll focus on him first, and then I'll put those other two guys back up on the board, okay? Sorry, I didn't make that clear. Plato believed in a timeless, unchanging cosmos. It was immutable, always was the same, or that it reproduced with cyclic behavior. The planets were themselves perfect spheres. They were perfect spheres with no blemishes. They were almost like these abstract, formless. This is what a planet would be to Plato, right? A perfect, faceless sphere. And he believed they were perfect geometrical shapes. Kind of weird if you think about it, right? Because let's go there. If the Greeks believed that these planets were their gods, Jupiter and Saturn and Mars, how weird is it that your God, that you're worshiping this abstract sphere? It kind of reminds me of like the Stanley Kubrick movie 2001, where the monkeys are all worshiping the outer space obelisk. To worship a geometrical object is kind of wild and cool.
If you think, I always thought about it, it's because for me, the circle is like the perfect shape.
And keep going.
Because it's for me, it's a perfect shape, and it's also a self-sustainable shape. It doesn't need anything else to be a circle, like the square. A square has sides, so it needs each sides to be a square. While the circle is just like it's never ending. I don't know if it makes sense.
Well,
That's
it made sense to Plato because he basically argued the same thing. He argued that the orbits of planets absolutely must be perfect circles. And his take on that, who is talking to me then? I'm trying to get used to your voices, but
Lionel.
Oh, Lionel, that's right. Sorry, I should know you now, Lionel. Lionel, his idea about the orbits of planets being perfect circles is something like this. Imagine that the orbits were not perfect circles. If they were not perfect circles, the orbits would not reconnect on themselves. And over time, after many cycles, the whole cosmos would become unwound and it wouldn't behave the way we see it behaving. His argument is, think about it. If you see the teapot in Sagittarius and you see it at midnight every summer, and your poppy saw Sagittarius at midnight, and your pappy's pappy saw it at midnight as well, as far back as anyone remembers, Sagittarius always returns perfectly in the summertime to the sky at midnight. The only way it could do that for thousands and thousands of years without becoming unhinged is if the orbit was a perfect ideal circle that reclosed on itself. So his argument.
Is that your theory of astrology?
This would be considered, well, okay, if you go back in time, there was no difference between astrology and astronomy because science hadn't really been developed as a concept yet. And mystical beliefs. I
meant kind of like as like of now, as more feeling like you agree with the theory of astrology or astronomy more.
Well, I'm an astronomer, so I certainly do not subscribe to any astrological beliefs. Those would be offensive to any astronomer.
I figured.
But I think this thing that Plato is doing was actually more like modern astronomy for this reason. Plato was trying to develop a theory of the cosmos that was related to observations in a way. I mean, Greeks didn't believe in observing and testing hypotheses, but he did believe by thinking, by abstract reasoning, that the orbits of planets had to be perfect circles for the heavens to be timeless and unchanging. Unfortunately, this idea that the planetary orbits must be perfect circles influenced astronomers for thousands of years after him, and it was very hard to break that concept in people's minds. Okay, one thing that might challenge the Platonic way of looking at the cosmos, one little fly in the ointment that's related to observations, and you guys can probably guess what it is, right? Is, where's the damn picture? Is right here. It's retrograde motion, right? How can the orbits of the planets be perfect circles if we see them doing these crazy loop-de-loops? Well, the student of Plato, Aristotle, was famous for not only believing in some of the ideas of Plato, but taking them to the next level in his attempt to build a working functional model of the solar system. And that made Aristotle a bit more sciencey than some of his contemporaries. Along with his friend Eudoxus, Aristotle and Eudoxus developed a model of the geocentric solar system that satisfied Plato's requirement for perfectly circular orbits, but also attempted to reproduce retrograde motion. Allow me to introduce to you the epicycle. The epicycle was a secondary circular orbit on which the planet was spinning backwards. And you can see the little animated GIF here. The red planet is on an epicycle, which is the red circle, and that's rotating backwards on top of the primary orbital circle. And by adjusting the rate of rotation, you can occasionally make Mars go into retrograde motion, while also preserving Plato's conceptual dogma that the orbits of planets had to be perfect circles. And this is where we get to Aristotle here. Hold on, may I erase this stuff? Is that okay? All right. Aristotle agreed with Plato's description of the universe, and he even attempted to improve it by building a working model of the cosmos. The cosmos, the solar system, whatever you want to call it. And he wanted to build a working model of the cosmos to reflect the actual observations of planetary motion. This, hey Jordan, would you mind turning the heat down to 70? Because I'm roasting alive in here. Sorry guys, I'm starting to burn up. A working model of the cosmos that would reflect actual observations of planetary motion. So of course, he used he in fact argues strongly for a geocentric solar system. And I have to go through some of his arguments because they're quite sophisticated. One in particular I need to talk about. And he also developed a model using, here comes your other big vocab word, epicycles. And to define epicycles, it's a second purely circular orbit on which planets rotate. And used to describe retrograde motion. Believe it or not, students, Aristotle's model of the solar system roughly worked, and he could actually predict approximately the rising and the setting times of Mars and the other planets. I think his model used something like 70 or 80 rotating circles. So his was considered more humble than the ones that were to come after it. But Plato's, excuse me here, I'm just trying to get control of my Zoom. Oops, I don't know what I just closed, but hope it wasn't that important. Where are you guys? My mouse is acting up. I think my batteries are dying here. I want to stop screen share. There we go. Okay. So, so the number of objects that we have to keep track of in the Greek solar system are the sun, the moon, 5 planets, that's 7, plus the background stars are 8. And basically Aristotle needed something close to 80 epicycles for his model to work correctly. Aristotle kind of set the ball rolling, and he set the stage for our third Greek astronomer. And forgive me for going through this so quickly, but I have to because I'm running out of time here. At least we'll get through Greek astronomy today. The third astronomer came after, hundreds of years after Plato and Aristotle. And Ptolemy was a mathematician astronomer, sort of a polymath who had many different skills. And his contribution, his fame in astronomy, is that he developed a sort of perfect working model of the geocentric solar system. In fact, Ptolemy's improvements to the Aristotelian model of the solar system were so significant that now we call the geocentric model of the solar system the Ptolemaic solar system, rather than the Aristotelian or the Platonic one. Ptolemy actually gets credit for making the bloody thing work, which was actually kind of dangerous because it wasn't philosophically correct. Preston, what are you thinking? Sorry, Preston, it says that you raised your hand. If you have a thought or you want to
Was
comment.
this the most generalized theory among all the astrologers, or which one was the most accepted that we're supposed to be able to compare and contrast them to?
This one. This was the model.
There's only one.
His model was so good that it
That
predicted.
only look at one geocentric model because it's so perfect.
Yeah. In fact, Ptolemy's model of the solar system was able to predict the times of eclipses down to
What
the
other
day.
theories are there?
Okay, that's an interesting question. There was actually another Greek who came before Ptolemy. He was a contemporary of Aristotle's. And I was going to blow past him because I didn't really have the time. But since you're asking, there was an ancient Greek astronomer named Aristarchus who made calculations and estimated the size of the sun and the moon based on geometry and concluded that the sun was like, I don't know, 400 times bigger than the moon. And based on that argument, he argued that the sun should be the center of the solar system. He actually developed heliocentrism thousands of years before Copernicus came up with it. So that would be a contrasting or a competing model to the Greek Ptolemaic model of the solar system. Yeah.
What about the other one?
Sorry? Sorry, Preston?
Your other theory?
Well, the two main theories that we're trying to compare today are geocentrism versus heliocentrism. Unfortunately, we'll have to save heliocentrism for next time because I'm running out of time. But those are the two main theories. Aristarchus was weirdly a heliocentric theory. Other theories are probably not even worth getting into because maybe they're like some flat earth stuff, and I wouldn't even know where to begin with that. In the history of astronomy, we focus on geocentrism versus heliocentrism because it tells an important story about the development of science. Yeah.
Are we going to get quizzed or labbed or given the answers to the rest of whatever
Oh, yeah.
you said about the theories?
When I tell you that there are 3 philosophers, that means the only things that I would test you on are the things that we're taking notes on: Plato, Aristotle, and now let's take a couple of quick notes on Ptolemy.
Did they all follow geocentrism or heliocentrism as
these
far
are
as there
all-
being 3 different astrologers?
These are 3, and I think astronomers would be fair to say.
Oh, okay.
Because what they're doing here, what we're focusing on is not so much the mystical side of things, although I'm sure that was there too. We're focusing on the astronomy part, the part where they actually made important. In a way, all of these guys had to come first,
Didn't
and
you say 3 astronomers?
yeah, and the third one is
Okay.
Ptolemy. So can I-
Right. Are they geocentric or heliocentric?
all geocentric.
Gotcha.
I promise I'll
They're
let
all
you know.
geocentric,
These are all geocentric. So let me.
so they don't have different theories.
Well, they all had the same theory, but they were modifying it, right? So let's take some notes on that, and maybe that will help. Okay,
All right, I'm gonna go with all 3 are geocentric.
that's correct. Yes. So Ptolemy, and we'll spell it out, he perfected the geocentric model of the solar system. This is the most important thing. Okay. He was in Arabic, Greek.
Are these the notes we already have from the beginning?
Nope, these should be new notes, unless I've lost myself. Arabic, Greek astronomer. He developed a model that used over 100 epicycles. So
Can I
his,
use the same PowerPoint here to find these same notes? Or do I need a textbook or something for this? Or like Google?
well, all or any of the above. I'm trying to design the course so that you guys can just survive with my notes. But
How we learn.
you will find this in chapter 3 of the textbook, and you will also find slides for this in my PowerPoint presentations. So all
Okay.
3 have, and they're similar notes. I don't know, you know.
Is the textbook that you give for the course considered in the syllabus, or would that just be
Yeah,
whatever
yeah,
there
I
is
went
for
over
the
that in the
course?
first day, but I haven't been back to CCRI because of the pandemic. This is
Right,
an
'cause they
old,
weren't
this is an
required
older
yet.
edition, but it's the cosmic perspective, the solar system component. That was
Okay.
the book that I recommended. And you will see that if you read chapter 3, these lecture notes that I give you are a
I didn't
condensed
attend this
version.
one.
So you will find consistency there, Preston, I promise you. Okay.
Well,
This
all right, it's
model,
either of the 3, I guess.
yeah, any or all of them.
All right.
This model of the solar system was so good that he wrote a book, and Ptolemy's book is called the Almagest, which is I think it's Arabic for the star or something like that. And the Almagest was the official textbook of astronomers that was used for the next 1,500 years, approximately. Because Ptolemy's model and his ephemeris table could actually predict the rising and the setting times of planets and the dates of eclipses for hundreds and even thousands of years to come. It was so good that people believed in whatever it was, like 50 AD or something, that they had solved the problem of astronomy, that they understood how the heavens worked. And there was no reason not to believe it, because if someone says, I'll tell you how the cosmos works, and by the way, next Tuesday, there's going to be a partial solar eclipse. If that happens, you tend to gain confidence in the person who's saying those things to you. Now, I think it's hidden behind my board here, but I actually have a copy of this book, the Almagest, in my bookshelf, and it is insanely dense and complicated to read. I have an advanced degree in astronomy, and I found it a challenge. It's not a stupid or a simplistic model of the solar system. Yeah, Preston.
Can you fix your terminology as far as the heavens when you say describing the rising and setting times of planets as far as gods between astrology and astronomy? Or is that too hard of a question? Because that doesn't seem very in context to anything.
Well, it's not a hard question. It's just not a relevant question because
Okay, I figured.
the God parts of it are
Never
not of
mind it.
interest to us here, really. I mentioned that only because it was important for them to work on this problem for reasons that went beyond what we would think of as science. But we're focused on modeling the planetary motions, and that's sort of that's the scale that we're looking at it from. We're thinking about it from an astronomy point of view. For instance, one last thing that I would like to do, because it will cue us up nicely for a discussion of heliocentrism next time, is we want to take one last set of notes before we end class on Aristotle's argument for a stationary Earth. And I think I have just 2 minutes left, and that should be all I need to quickly jot this down. Everyone, I'm going to erase this stuff, so if you have any objections, you got to let me know now. Sort of to close off our discussion of geocentrism, I'd like to take one last little bit of notes, and that's on Aristotle's argument for a stationary fixed Earth. In other words, an Earth at the center of the cosmos that does not move. And it's a pretty sophisticated argument that affected astronomers many, many thousands of years after Aristotle's life. So because and thanks to Preston for bringing this up, Preston asked, were there any contrarian theories during the Greek period, theories besides geocentrism? And the answer is yes. There was a weird version of heliocentrism that was proposed by Aristarchus. And perhaps in an attempt to address why this theory could not be true, Aristotle developed a detailed and sophisticated geometrical argument for why Earth should be the center of the cosmos. And it's a picture. We're going to draw this picture. Let's say, argues Aristotle, that Aristarchus was correct. And let's say that the sun was the center of the cosmos and that Earth were to go around and orbit the sun. It would look like this. However, remember that outside the orbits of all the planets, in the Greek geocentric model, the final sphere that rotated around the cosmos was a fixed sphere of stars. And what I'm going to do now is I'm going to put 2 stars on this sphere, all right? So we'll put a star over here, and we'll put a star over here. We'll call this star A, and we'll call that star B. And those 2 stars have some angular separation on our sky. If you want, you could think of them as the stars in the belt of Orion or something, which are separated by a degree or 2. Aristotle's argument goes like this. Imagine that Earth did go around the sun. That's fine, Ethan. Thank you very much. And Ethan, this homework will be new. It's not something we did in 1020. So definitely get back to that video. And I'm almost done here, guys. Just give me a sec. When Earth was in this position on its orbit, when it was close to those background stars, the angular separation between the 2 stars would be 1 angle. And I'm just going to call it alpha, because that's a Greek letter, right? And then, argues Aristotle, if you were to wait, say, 6 months from now, imagine looking at those same 2 stars. They would now make a new angle. And if you guys remember how the small angle formula works, if the distance between the stars is fixed, the farther and farther away you are, the smaller and the smaller the angle between them should get. So now, 6 months later, they have a new angular separation, which is beta. And you can clearly see from geometry that as Earth gets closer to and farther away from the stars, that the angle alpha must be greater than beta. And what that means is that over the course of 6 months to a year, if you keep track of two stars in the sky, blue star and green star, if Earth moved during the year, you would see their angular position on the sky grow and shrink as Earth got closer to the stars. This is closer, and farther away from the stars. However, Aristotle argues you can look at all of the stars in the teapot, in the belt of Orion, in any old constellation you want. And Aristotle argues, I have never seen that happen. I have never seen the angular positions of the stars change, and they would have to change if Earth changes distance. And the more sophisticated version of this, we call it parallax. And I'm going to use this as an opportunity to introduce one more vocabulary word. The gist, or the simplest way to explain Aristotle's argument, was there was no observable parallax, where I will now define parallax. Okay, thanks, Marissa. No observable parallax, which is an angular shift in the position of stars due to the motion of Earth. This, okay, Priscilla, take care. Watch the homework later. I know some of you have to leave. This is a very powerful argument. It uses geometry. The argument is clear and easy to understand, and it would have been very difficult for any person in Aristotle's time to really mess with this argument because it's based in observation. It's actually good science in a crazy way. Now, just for fun, as we end our lecture here, does anyone see the one flaw, the one place where Aristotle went awry? And this picture is at the heart of it here. Aristotle's argument is so good that it's almost unfair. It's almost hard to see where the flaw, what the assumption was that turned out to not be correct. Would it be obvious to you guys what the flaw or the assumption was in Aristotle's logic? Well, let me tell you, since we're running out of time. Aristotle would be correct if the background stars were just a teensy bit further away from the Earth relative to the planets, right? If the stars were close to us, we actually would see this type of parallax effect. But what Aristotle couldn't wrap his mind around was that there would be 7 astronomical bodies, sun, moon, and 5 planets, and then this huge empty gulf of nothingness for dozens of light years until you even get to the next star. The fact of all this empty space in the cosmos wouldn't have made any sense to the Greeks. In fact, believe it or not, stars do undergo parallax, but it's such a tiny displacement that the first measurement was not done until the 1850s, and it took a very powerful telescope and observations over an entire year to be able to detect it. Okay, so let me go to—
What other two were the geocentric?
what other 2 philosophers you mean? When you say what other 2, I just want to make sure I understand. You mean what other 2 philosophers were the geocentric philosophers? Aristotle, Plato, Aristotle, and Ptolemy. Those were the 3. Okay. Okay. We're going to have to work on a homework now. We'll take a little pause. I think, what do we usually do? About 10 minutes or so, and then we'll begin homework number 3. Does everyone feel good about that? Okay.
Yeah.
All right. So let me just say that we're a little behind. It's 1:07 iPhone time. So maybe, I don't know, somewhere between 1:15 and 1:20, I'll come back and we'll crank out the homework as quick as we can. Today's will not be as hard as last week's, I promise. Okay. All right. See you guys in 10 minutes. Take a break, get some iced tea. Okay, Astronomy 1010. We're back and it's time to do homework number 3. Unfortunately, I got about halfway as far as I planned on. We did the geocentric astronomers. We did not get to the heliocentric astronomers. I will cover them on Monday, but we are going to have to do a little bit of Kepler's laws in today's homework. The good news is the formulas are simple and I can show you how to punch them into your calculator. And it might actually be better this way. You'll kind of practice punching the buttons and then we'll think about what it means more on Monday. So let's get into this here. Let's share our screen and let's pop on over to Blackboard. And we'll go to our homework tab. And we're doing homework number 3 today, problems from chapter 3. And if you right click and open that PDF, I'll have you guys read some questions while I put the answers on the board for you. Okay. Let's see, Ethan. Wait, no, Ethan's not here. Or Mateo, can you help read the question? I just need you to read these numbers out to me while I'm standing in front of the board. Okay. So let's go here.
Okay, so it's going to be chapter 3, problems 48, 49, 52.
Mateo, sorry, just one sec, buddy. Don't forget to format your homework in the following way. Name, AS1010, and then please put your section. You're either 001 if you have the, Monday lab. You're 02 if you have the Wednesday lab, and then you're 101 if you're in the night class. And we're doing homework number 3. Very important to write that down. Okay, Mateo, now I'm ready for the numbers. Chapter 3.
Problems 48, 49, 52, 53, and 54.
48, 49, 52.
53 and 54.
Okay. So Mateo, since you're on the ball here and you're reading, are you down to read chapter 3, number 48 for me?
Yeah, one sec. Right here. Oh, Chinese calendar. We talked about it on Monday.
Yeah. I really like this problem.
The traditional Chinese lunar calendar has 12 months in most years, but adds a 13th month to the 22nd of every 60 years. How many days does this give the Chinese calendar in each 60-year period? How does this compare to the number of days in 60 years on a solar calendar? Based on your answers, oh, should I keep reading? There's no one.
Yeah, might as well. Just
based on your answers, explain how this scheme is similar to the scheme used by lunar calendars that follow the Metonic cycle.
Metonic cycle, which is a lunar cycle.
Okay.
So let me help translate some of this for you guys. Our calendar, the Gregorian calendar, is ultimately a solar calendar because our calendar attempts to account for the fact that there are 365 and a quarter days in a year. So we have a calendar which has roughly 365 days in a year, and we use leap years so that every 4 years we add a day in February. That makes our calendar solar based, and it's based on the number of days in a year. But other cultures, including the Chinese calendar, Jewish calendars, and Arabic calendars, actually use lunar cycles to keep track of time. And the point of this problem is that both are completely valid methods of keeping track of a year. So the way the Chinese calendar does it is in a 60-year period, most of the years are 12-month years, like our Gregorian calendar. But on 22 out of every 60 years, they add a 13th month. So let's start with that data on our board, okay? So 13th on 22 out of 60 years. And that means 60 minus 22 will give us what, 38? Did I do that right? Yeah. 38 years out of 60 years. Yeah, okay. Now, what we're supposed to do is we're supposed to calculate the number of days in 60 years. So it says, how many days will this give the Chinese calendar in a 60-year period? Now, to convert from years to months to days, it gives us a hint, and it tells us that we're going to need some of the data from problem 47, which is also on the Metonic cycle. The Metonic cycle is the lunar cycle. So they tell us here that the moon's monthly cycle of phases, which we call it Synodic period, is 29.5306 days per lunar cycle. And let's take that down as a conversion factor. So 1 month, I usually use MO as an abbreviation for month, is equal to 29.5306 days. I usually put boxes around my conversion factors. Because this also ties into our lecture concepts, let's remind ourselves that this is a synodic month, because this follows the phases of the moon rather than the true orbit of the moon. Okay, so this should be all we need to calculate the first question. The first question is to find the number of days in 60 years for a lunar calendar. Before I show you how I think we're going to do this, would you guys know how to do this if I wasn't here to help? Would anyone even know how to start? I'm kind of curious to see what methods you guys might use or how you might think your way through this.
I mean, I don't know, multiply 29.5306 times 12 and then add it to multiplying that to 13, because you want to see how many days there are in 60 years in a lunar calendar. Am I wrong?
You're not wrong. You could kind of do that, but remember, we have to have some years with 12 months and some with 13 months.
Yeah, that's what I meant. Like multiply 1 month, like the 29.5306 times 12, and then multiply that same number. Like multiply 29.5306 times 13, and then add the results of both.
Yeah, Matteo, that actually would work, and that's it's an okay way to do things, although there are potential places where we can get messed up. After a lot of time thinking about what the best way to do this problem was, I eventually came to the Preston. Yeah.
I don't know if I'm mistaken from what he was trying to say, but I think what he was looking to do was multiply 12 and 13 by 29.5306 and then take the difference of the two totals and then have the difference be the remainder to 12 times the 29.5306 days to equivalent the amount of days within a Chinese New Year.
Definitely multiplying these by 12 and 13 is good, but the difference, by which usually one means subtraction, we're not going to take a subtraction here.
Okay.
Probably one of the most elegant ways to do this, so part of this is I get to show you guys another method, is let's first just start off by finding out the total number of months in a 60-year period. So that ends up being the cleanest way. And of course, you guys know I love dimensional analysis, so I'm going to want units to play a big role here. So let's write this down. First, find the number of months in a 60-year period. By the way, the first time I ever solved this problem, I did what you guys did. Your first instinct was also my first instinct. And I discovered it actually got a little bit confusing as I went deeper than that. This eventually I settled on as the best way. Find the number of months in a 60-year period. So we have, let's see, 12 months per year. And that was the real secret, is to realize it's 12 months per year. And that's being multiplied by 38 years. So this will give us the number of months in our 38 years that are 12 month. And then we do plus 13 months per year multiplied by 22 years. It was very important for me to be able to see units in this process. Cancel out years. Cancel out years. Our final answer will be a total number of months. So let's take out our Casios and let's do that. So we have 12 times 38 plus 13 times 22. And that brings us up to 742 months. The nice thing here is that we've kept everything in terms of months, but there is only one conversion factor from month to year. That's what ultimately makes this a more elegant way to do it. Instead of trying to then figure out the years once everything is in days, that ends up being kind of messy. Okay, so how should I do the next bit? Matteo?
You just multiply the 742 times 29.536.
Yes, but let's do it dimensional analysis style, okay?
Oh, so it's 742 months over 1 day.
What? Nope.
Oh.
It's 742 total months. And then remember, this is the conversion factor. So in dimensional analysis, we put our conversion factors first units and then numbers, right?
Okay. So 1 month goes, yeah, that makes sense. You put 1 month in the bottom and then 29.5306 on top days.
Yep. My only small critique, which you might not think is a big deal, but I do, I would set it up with the units perfect first. Then I'd slap in the, basically exactly what you said. But first I put in the units, then I put 1 next to the month. 29.5306. Hey, Matteo, while you're at it, how many sig figs do you think I can keep in my answer?
Three.
Actually,
Because you have to.
742 is not a measurement. It's a perfect number of months. See, in the lunar calendar, they define exactly 12 months in 38 years and exactly 13 months in 22 years. The measurement is here. It's actually in the conversion factor. And the 29.5306 actually has 6 significant figures. So this is a much higher precision answer than we're used to. So let's multiply and let's round to 6 sig figs. Matteo, did that make sense to you about the perfect 12 months? Or that might have sounded weird if
No, that makes sense.
okay, all right, good. All right, so 742 times 53, sorry, 29, backspace key comes in handy, 29.5306.
Is this what's supposed to come out? I know it's backwards, but
Let me see. Ethan has the same number I do. Who was that you, Ethan? Was that what you're? And Daniel, looks like you've got it too.
it's Daniel, yeah.
Yep. So Cole and Ethan and John, you guys all have the right number. You've got the same number as me. What should we round it to?
To 0.7.
That's right. That should be 6 significant figures. So 21,911.7 in my units.
Months.
Days.
Or days. Yeah.
Days, because months are canceled. So 21,000.7 days. Okay. This is half the problem. This is for the lunar calendar. Next up, they ask us to find the number of days in a 60-year period for the solar calendar and then to compare. Has everyone caught up to me? Or-
Oh, I'm sorry, I didn't mean to laugh. I was
Got
reading
you,
something.
Mateo. We heard you. We caught you laughing. -2 points. Okay. Does anyone need another second? I'm gonna erase like this stuff. All right.
Would you like us to copy down all that work and submit it?
Oh, hell yes. If you
Okay.
don't give me all this, I take off points.
Yeah, I figured.
This plus the next thing we do is all part of this answer. So do you want a minute?
Yeah, that would be great. Thank you.
That's fine. Take your time. I can sip some coffee from my secretary, right? Oh, John, is that, I remember he's got a really heavy metal name. What's that kitty's name? Wait, Charles Manson, right?
Yeah, Charles Manson.
Yeah. He's a, what do you call it? Mancoon?
He's just a regular cat.
Yeah, he looks like our cat. Except our cat is really fat. It's 25 pounds. Yeah, Charles Manson doing the astronomy lunar homework. Okay. That's cool. So that's your roommate's cat, right? But he seems to like you, John.
Yeah, he comes by. I got the treats.
Here's mine is over there, sleeping on the
Oh yeah.
Garfield
surprised he-
much?
I'm surprised he doesn't bug me more often. As soon as the lecture ends, he comes up to me and starts meowing for treats. Okay, next up, we're going to do the solar calendar. I'm going to erase some of this stuff. I'll leave that answer down there. So in the next part of the problem, we're going to compare to 60 years in a Western-based solar calendar. The beauty of the solar calendar, or the drawback, is we don't consider months. We're not concerned so much with the moon cycles. It's not metonic. It's solar-based. So in that previous problem, we also need this conversion factor. The length of what's called a tropical year, which is the time from spring equinox to spring equinox, is 365.2422 days. So let's write that down. It's what's called a tropical year. A tropical year is a calendar year. It's the time from spring equinox to spring equinox. And that differs from the true sidereal year by about 20 minutes. So in a tropical year, 1 year is 365.2422 days. In a sidereal year, it's 365.25, and I forget what the other digits are after that. I could probably look it up. And the difference has to do with Earth's precession. I wanted to get into that during lecture, but I lost it. Sidereal year should come right up here. A sidereal year, I was hoping 365.256363004. Craziness. Timekeeping is wild, guys. It's very deep. Okay, so this is going to be easy. We just take 60 years. We're going to go from years to days, and our conversion factor is right there. So we have 365.2422 days to 1 year. Now, how many sig figs should I keep, Mateo?
Seven.
Yeah, but hear me on this one too. This is another weird thing. I know. There's always a thing, right? Yes, we are justified in keeping 7 significant figures because of the conversion factor. But don't forget, Mateo, that they want us to compare to the lunar calendar. If there's one thing that I've learned, it does not make sense to compare 2 numbers with different levels of precision. So even though we could keep 7 fairly, we are going to round back to 6 so it makes a nice, pleasant comparison. So give me your final answer to 6 sig figs.
21,914.5.
Days, right?
Yeah, days. I'm so sorry. I hate to be this person, but someone has their mic on and they're typing, and I have my headphones on.
Sorry about that. Yeah.
Now, you'll notice these numbers are close, but when we compare, close is not acceptable. We want to do something quantitative. And my recommendation is what we're going to do is we're going to calculate.
Daddy.
Sorry. Don't forget.
What was that?
I don't know. No comment. Okay.
I didn't even mute on my phone.
Right,
It's not normal.
No, fuck.
Yeah, that's absolutely scary.
Percent
No, ain't no
error.
way.
Percent error. We're going to calculate the
I
percent.
was like uncomfortable for everybody.
We'll get over it. We'll get over it. Come on. Percent error is this. It's the difference between the two answers as a fraction of the true answer. Now, here, there is no true answer. The solar calendar is every bit as valid as a lunar calendar. But since we're used to using a Gregorian solar calendar, we'll use that as our reference. So the way they sometimes represent percent error is it's the absolute value of your answer minus the true answer as a percentage over the true answer. Now, what your answer and what the true answer is can be a little bit shape-shifty. It's basically the difference as a fraction of one of these big numbers. So what we'll do is we'll do, let's see, this one's a little bigger. So we'll do 21,914.5 days minus 21,911.7 days, put parentheses around that, and then we'll divide it by 21,914.5 days. Okay. To do this, we should use our parentheses.
Wait, I'm sorry. If you're putting the our day, no, it should be divided by 21,911.7, because if you're putting.
Yes, I know what you're saying, Matteo, but you're being too literal about your answer and true answer. In fact, I probably should not have wrote it this way. It's just that I've.
Well, I'm just following the equation.
I know you are, and yet it honestly won't matter very much which number you put down here. But let me tell you the way I'm thinking about it. I'm looking at the difference, the change in days, divided by the number of solar days. What I said, Matteo, is I've decided to use the fraction over the solar calendar because that's the one we're more used to, since we live in a society, or at least the United States is based on a Gregorian calendar system. I actually could do this over the lunar calendar day and be fine.
Does that do percent error for which calendar?
I guess it's with reference to the solar calendar. That's why I put the number of solar days down here. So in other words, why don't we get the answer and then I'll help us to understand.
Does it work the same for the lunar one too, or no?
We can actually compare them. It'll be so close. Let's try it. So let's do this. So let's do 21.
We don't have to switch the difference.
No, we don't have to, because it's an absolute value sign. You always want it to be positive. Okay.
Where?
So if we switched it, it wouldn't change things because it's an absolute value. It's 21,940.
You don't have an absolute value.
Well, you just
unless you mean it to be on your numerator.
The absolute value just means you get rid of the negative. So 21,914.5.
And your lunar, your solar.
Minus 21,000, just follow me for a second and then I'll help explain. 911.7. So the difference in days is 2.8, right? So it's basically 2.8 days divided by 21,914.5 days. Now, that is, and we're going to round hard here, 1.3 times 10 to the negative 4.
Aren't you going to multiply that by 100 since it's a percentage?
I'm getting there. Just one sec. First, see, Matteo, I am very comfortable thinking of raw decimals. I don't even, yeah, multiply by 100, but let's just write this out. 0. So I need the 1 to be in the 4th place. 1, 2, 3, 1, 3. That's the raw fraction. And yes, as Matteo points out, we multiply by 100 to get the percentage. So that would be the same as 0.013%, or to say that in plain English, 13 thousandths of 1%. Now, Preston was also saying, what if it was compared to the lunar calendar instead? If we divided 2.8 days, the difference, by 21,911.7, you would actually still get the same thing. You would get roughly 1.3 times 10 to the minus 4. So it actually, because basically it's a 2 to 3 day difference out of 20,000 days.
Your significant figures are wrong.
How do you follow? I intentionally rounded this hard. I did not keep a 6 sig fig answer, because when it comes down to a percentage, in that case, I'm interested in a zoom out big picture thing. And I'm trying to get a rough sense of what kind of a difference there is between the solar and lunar calendar. The point is, and let's not lose track of the point. The point is the number of days are wicked close, to say it like a Rhode Islander. Both are perfectly valid calendar systems because they only differ from each other by 13 thousandths of a percent. They're both keep good timekeeping over a 60-year period. And that's our final answer.
But that's strange though, because if you look at it in a year, you wouldn't think that they're close.
That work does not add up at all.
Well, see, but remember, Matteo, close depends upon how many days you're counting. Look at it this way, Matteo. If you and I were both dead broke and I owed you $2.80, that might be a big deal, because that might mean we could get a cup of coffee or something.
Like when you only talk about the moon and the sun, clearly there's no other way to look at it.
Well, these are the two main calendar systems that human beings use. I know.
How do you do it the other way, since you knew how to do it with the lunar one too? Because you couldn't explain this one.
Well, I'm not sure what you're asking, Preston. I did show you that you get the same answer if you compare it to the number of days in a lunar calendar.
But exactly wrong.
What do you mean? What? Guys, yeah, I punched the numbers in. If you do 2.8.
No, I know what you're saying. I think he's referring, when you said
maybe I carried a decimal. I might have carried my work wrong, is what I'm saying. I tried to follow it like flashcardedly, I think, and it didn't work for me.
What?
I think I remember when he was saying the numbers. What's it called? After the decimal, I forget the name. You see where he got the 2.8? That's because he just subtracted the 21,000. That's why we only get two significant figures.
That one, the significant figures for the solar and lunar months, I think, were the ones there that hadn't made sense because they were off of different units, and then finding the difference after not looking for the difference was supposed to be the split. And 2.8 doesn't really make sense for a difference in a month that you're multiplying by so many units compared to a different product when it's like month wise, because clearly it's like 29.5 and then the 365 for the 1 year. and then it's a different total. So I think it's just working on a different scale.
Yeah, I'm not really sure what your comment is here, but it is true that these are the number of days in each calendar. It is true that they differ from each other by only 2.8 days. And the only point, we don't want to get lost in the sauce here, is that 3 days is a very tiny percentage of 20,000 days. That's it. That's all we're trying to say is being off by 3 days out of 20,000 is not bad. That's good. That's impressive. Anyways, we can debate this all day, but sooner or later, we're going to want to have dinner. So why don't we just take it down, move on, and we'll go on to question 49. May I erase? Does anyone need another minute, or can I erase? I'm erasing. All right, chapter 3, number 49. Who's next in my box there? Ethan. Ethan, can you read 49 for me, buddy?
Hold on.
I think it's known as it's called the method of Eratosthenes. Another Greek.
No, it just logged me out of CCLI. So
Okay, that's okay. Ethan, John, do you have the questions up, John Putagano?
I have the printout of the
I got
exact file. So.
Guys, there's a madman shouting in the streets.
Shout back.
Oh my God.
Take us with you. Let us see it.
you can hear
Yeah, I can hear
in
it.
the
I know
background.
what
All I could hear was a very silent. Ah.
the joys of living in Providence, I guess.
Guys, I'm so sorry, but that guy was right outside my window and he's going, da, da.
Yeah, you could hear it.
But he's pointing at the sky and he's pointing in different. It sounds like he objects to my astronomy lecture as well. Everyone's a critic today, okay? All right.
Well,
That is sad.
I did manage to get up the PDF at least.
Okay, Ethan, why don't you read me the method of Eratosthenes?
You are an astronomer on planet North, which orbits a distant star. It has recently been accepted that North is spherical in shape, though no one knows its size. One day, while studying in the library of Alec-town, you learned that on the equinox, your sun is directly overhead in the city of Neen, located 1,000 kilometers due north of you.
All right, they actually,
I'm just making sure that you're getting everything.
you know what, Ethan, there's actually a small problem with the way they wrote this question. It's a little kooky. So here's what we're going to do, guys. Get yourself a good circle maker. Maybe for your paper, something about, about the size of this tape circle. Something about.
Will a dollar coin do?
I think a coin will be too small. It's got to be like closer to the size of a coffee lid might be pushing it, but it's got to be bigger than a coin. Because we need to make a geometrical diagram so that you can understand the method of Eratosthenes. Here's what we're going to do.
Does large shot glass work?
A large shot glass would probably be perfect.
Okay.
Even a coffee cup. Oh yeah, that bottle, Matteo, probably a pretty good size. Leave yourself a little bit of headroom, and I want you to make the circle down here. Once you've drawn your circle, try to put a dot as best you can right at the center of the circle. And then we're going to identify. Then we're going to identify 2 cities. Okay. Someone's beeping. I don't know what the beepies are, but quit your beeping. Is that you, Ethan? All right. in the story of Eratosthenes, he was a famous Greek who actually successfully measured the circumference of Earth using only geometry and a couple of sticks. Eratosthenes had lived during his lifetime in two cities. One was the city of Alexandria in modern day Egypt, and the other was a city called Syene. They changed the name of the city to Nain in this problem, but it's clearly referencing Syene, that this ancient city. And Eratosthenes had lived in Syene as a young man, and then when he was an older scholar, he moved to Alexandria, which is where all the modern day learning was at the time. Now, as I tell you the story, we're going to flush out a diagram together, okay? First, draw a line from the center of Earth up to Alexandria, and then we're going to extend it out to put a stick into the ground. So something like this. We're going to draw the radius of Earth, but we're going to extend it out a little bit. And this was the stick or a staff that Eratosthenes put into the ground. Now we're going to draw another radius to the city of Nain or Syene. And we're going to place in the stick. We're going to place a stick in the ground over there. Okay. As the story goes, when Eratosthenes was a young man, he remembered that on the day of the summer solstice, when the sun was as high in the sky it could possibly be, he remembered that he could see all the way down to the bottom of a well shaft and could see water at the bottom of the well. But he noticed years later, when he lived in the city of Alexandria, on the day of the summer solstice, he could not see down to the bottom of a well because it was covered in shadow. And he knew that this meant that the sun actually was directly overhead at the zenith in Nain, but it could not get to the zenith in Alexandria because you were too far north. And he came up with an ingenious idea of how we could use this to measure the actual size of Earth without having to travel around it. First thing he did is he reproduced the experiment, but instead of doing wells, he now took two sticks, like 2 meter sticks, and he placed them perpendicular into the ground. And then what he did is he measured the length of the shadow on the stick that was in the north. The stick that was in the south, the one in Syene, did not cast a shadow. Why? Because the sun was directly overhead. What we're going to do is we're going to draw in some rays of sunlight together. First, we're going to draw in a ray of sunlight that goes in the same direction as the stick in the south. And this ray is going to be to the sun. And that means the sun is directly overhead in the city of Nain. Okay, next up, we're going to reproduce some astronomy specific knowledge. And this is where his brilliance comes in. No matter where you are on Earth, all rays of sunlight must always be parallel to one another. And I'm going to draw it first, and then I'm going to explain it second. Every person on Earth has sunlight coming from parallel lines directions. So if a ray of sunlight is directly over the top of the stick, a ray of sunlight striking the ground at Alexandria must be perfectly parallel to that ray. So this is also to the sun. This is not obvious your first time around, and it has to do with the fact that the sun is really far away in comparison to the circumference of Earth. Let me show this to you in a slightly different diagram before we proceed. To help you understand what I just said, remember that Earth is a sphere that's like over here, and the sun is a sphere that's over here. And rays of light leave the sun in all kinds of crazy directions. The sun is an isotropic emitter, meaning it's emitting rays in every possible direction that you can imagine. Some of those rays will be capable of reaching the Earth, and only rays which leave the sun in a parallel direction will actually strike the Earth. Imagine I constructed a ray that only deviated from these other two by 1 degree. Over the course of an astronomical unit, the ray would basically miss the Earth in its entirety because it would deviate from the parallelicity of the other two lines. So this is kind of an astronomy specific thing. An astronomer usually has to teach this to you. All rays of sunlight are parallel to one another. The goal that Eratosthenes had by measuring the shadow on the stick was he wanted to measure this angle here. I'm going to call that angle theta. And what theta is it's the angle between the zenith and the sun in Alexandria. The reason why he wants theta is because the real angle he's interested in is this angle. This is the angle between the two cities, Alexandria and Nain. And theta is also that angle, or the two angles are the same. Also, it's the angle.
What is your emoticon, lexicon, little?
This
That's a theta or theta.
This is not an emoticon.
Oh, your spelling.
It's a letter. It's a Greek letter, theta. And this is a tradition that mathematicians, physicists, and astronomers always use Greek letters to represent angles, sort of in honor of the Greeks because they love geometry, but also because you start running out of letters. It just helps with math equations and things.
No, I don't care for your symbols. I mean, like,
Well,
as far as like an
unfortunately,
anagram
you have
goes.
to because I'm the teacher, right?
No.
Like
No.
it would be very foolish of you to use your own symbols because then you might get yourself in a jam that I can't help you out of. But this is a standard practice, like I didn't make this stuff up. I'm teaching it to you the way that astronomers teach all of their students. All right, now there's a theorem in geometry called alternate interior angles. If you have two parallel rays and you cut them with a stick, this angle, the angle on the other side, this angle, and an angle on the other side there are all the same angle. It's a theorem called alternate interior angles. And if you think about it, it sort of makes sense. If your train tracks are parallel and a stick is a straight line, then all of these angles have to be the same. Now, I'm not going to prove that to you because that's the work of your geometry teacher. And I don't have time to reproduce all of that. You're just going to have to trust me that theta, the angle between the sun and the zenith, is also the angle between the two cities. If that's the case, it's possible to take some measurements and calculate the circumference of Earth. The two parameters that we're going to need here are the distance between the two cities, which I will call D, capital D. So D is the distance between the two cities. And the last thing that we're interested in is the circumference of Earth. I'm going to use the variable CIR, and that's going to represent circumference of Earth. All right. Eratosthenes knows that the ratio of theta to a complete 360-degree spin will be the same ratio or the same percentage that D, the distance between the two cities, is to the entire circumference of Earth. In other words, his starting point is theta is to 360 degrees as the distance between the two cities is to the circumference. And if you take a moment and think about it, that should make some kind of reasonable sense to you. For instance, let's go back to our whiteboard for a second. Let's clear all drawings. Let's grab ourselves a circle. If you think about it like a pizza or something, if you take a quarter turn around a pizza, that should be a 90-degree angle. And 90 degrees is a quarter of 360. The crust should also be a quarter of the circumference of the circle. And that's basically the ratio that we're trying to reproduce here. However, it does mean that we can do algebra. We can cross multiply and solve for the circumference of the circle. And if you do this, you get this equation. The circumference of your planet is 360 degrees divided by theta times the distance between the two cities. Both of these are observables. First, Eratosthenes measured the shadow, the length of a shadow cast by this stick, and that's how he measured theta. In his case, he got like 7 degrees or something. Then he paid his friend some money to travel the distance, to actually walk out the distance between the two cities. And by measuring the distance between the two cities, measuring that angle, he calculated the circumference of Earth. And we believe his answer was pretty close to within a 5% error. This equation here, and why we want to keep my symbols, Preston, is because this is how the equation, I'm going to give you an equation sheet for your exam, and you will have one question on the method of Eratosthenes. And to help you, this is how the equation is going to appear on your sheet, and it's known as the method of Eratosthenes. This is the problem that we're about to do, which is actually wicked easy. But I wanted the problem to be learning the method of Eratosthenes, which presumably you did. I want this diagram included as part of your answer for 5 points.
I just have a quick question.
Sure.
Like all of this is based on him determining that the sun was direct, like the rays, the ray of the sun was directly to 9.
This is a good, so let me help you say that a little better, Matteo. Yes, the critical thing here, one of the critical, there are several critical ideas to do this, but this is astronomy specific knowledge. This whole thing would break down if you did not know that all rays of light striking the Earth from the sun are always parallel to one another. And that is not an obvious thing. That wouldn't have been obvious to me the first time I studied astronomy. It's very apparent to me now, but it's one of those aha moments that we're supposed to have. All rays of light from the sun must always be parallel on the same day. And if you have issues with that, Matteo, we can talk about it more. I did give a little diagram description. I tried to explain it, but it may not have been sufficient to satisfy you. Let's take a peek real quick at the question again, because we kind of probably got lost during that. And this is question method of Eratosthenes 149. So now they've changed the names of the cities from Alexandria and Syene to these silly names, Nerth and Allectown. Okay, fine. But here are the important pieces of data that you were waiting for me to write down, Ethan. On the equinox, you go outside and you observe that in the northern city, the altitude of the sun is 80 degrees in the sky. They also tell you that there is a distance of 1,000 kilometers between the two cities. So those are our givens. The altitude of the sun is 80 degrees, and there's 1,000 kilometers between the two cities. But we have to be careful here. Let's go back to the board. In this problem, our givens are the altitude of the sun in the northern city is 80 degrees. The distance between the two cities is 1,000 kilometers. The 1,000 kilometers is d, the distance between the two cities. But this angle, 80 degrees, is not theta in the diagram. Can anyone explain that? Does anyone see why the altitude of the sun is different from this angle between the stick and the sun? Here's a hint. It might be good to remember the definition of altitude. I'm going to erase a few things over here so I can get a little board space back. Let's draw a picture from the perspective of the northern city in Alexandria or Alec-town.
Maybe I'm thinking too hard, but isn't the altitude of the sun depending on like where it's taken? Like the
I'm sorry,
the
can you
degree?
say that again, Matteo?
So here the given is the altitude of the sun is 80 degrees, but where are they taking like that measurement from? Because the altitude
that
would be different.
That is encoded in the definition of altitude. So Matteo, to answer your own question, could you read me the definition of altitude from like two lectures ago? If you scroll back to last week, I think it was last Monday or something, I should have defined altitude for you. It's under the horizon system when we talked about 3 coordinate systems.
It's the degrees above the nearest horizon.
Right. Now look at this diagram that I'm drawing over here, Matteo. The horizon, north or south, is like here or there, right? And the sunlight is where the sun is. And they're telling us the altitude of the sun is 80 degrees. And what that means is from the horizon to the sun, right?
Dang. Apologies for the disconnection. I have terrible service out here.
That's okay. I feel your pain and I understand. I live in fear of the day they shut my internet off.
I know. I was hoping that you'd be able to.
So my point is this, Matteo. We define altitude as the degrees above.
What did I miss there from the last one? Or are we still working on the last point as far as the two cities and stuff?
Yeah, we're still working on the method of Eratosthenes and we're about to get to the big moment here. What I would like to have is I'd like to have this diagram, this formula. I want this little sketch too, which is very easy to make. Basically what we're doing is we're taking the given, which is the altitude of the sun, and we're trying to figure out its relationship to theta. Theta is the angle between the zenith and the sun. So do you guys understand what I'm saying here? I'm trying to hint at what we're supposed to do.
Is it zenith 90 degrees above the horizon?
Always,
Really,
right? Zenith is straight up, horizon is sort of
okay,
flat.
so theta would be 10 degrees.
10, right. In other words, if the altitude of the sun, the degrees above the horizon is 80, then theta is the angle between the zenith and the sun. And the whole
Okay, that
point,
makes more sense.
and you came right back, whoever lost the internet there, you came back at the critical point. Theta in this problem is 90 degrees minus 80 degrees. The altitude of the sun is 10 degrees between the zenith and the sun. Now,
I think I worded my question wrong. When they give us the 80 degrees, like 80 degrees of the position of the sun or whatever, the altitude of the sun is not the same everywhere in the world. Like, I don't know if that makes sense.
that does make sense. So I think what you're worrying about is the altitude of the sun would be different from Nain to Alexandria, correct, Matteo?
Yeah, yes.
And that is correct. Remember, you should be able to tell me the altitude of the sun in this city because it's directly over the stick. What would the altitude of the sun be there?
At Nain?
Yeah, in Nain or whatever. Remember that the horizon is perpendicular. In other words, Matteo, let me help you. In Alexandria, this is the horizon there. Actually, I'm gonna do the horizon in green so I don't mess this up too much. This would be the horizon in Alexandria, right? But the horizon in Nain would be here. Right? And you are correct. The altitude of the sun is different in the two cities. In Nain, the sun is above the stick. That means it's at your zenith and the altitude would be 90 degrees. I think what you're getting confused by is I told you that all rays of sunlight are parallel. But you're getting worried that the altitude of the sun is different. And you're thinking, wait, how can the angles be different if the lines are parallel? Is that what you're saying?
Yes. How are you?
But
How is that happen?
Mateo, if you think really carefully, both of those things can be true at the same time.
What stick?
The rays of sunlight are parallel from space, as seen from a distant vantage point. On the ground, the altitude of the sun will be different, just like I told you at the beginning of lecture today. If you walk north or south on a planet, the altitude of Polaris will change. But it's still possible.
What are your vectors?
Pardon?
What are your angles? You have 1 theta, 2 theta, and 3 theta over 360 degrees without any other degrees to follow. And you have one whole circle. What more degrees could you possibly add to a full circle that you're solving for in that directional?
No,
that's supposed to be acute if you're not given any degrees by your smaller scale. I can't understand how 360 degrees is added to or subtracted if that's a circle.
No, you're just misunderstanding my diagram. I am showing you that a circle contains 360 degrees, which we already know, but the angle between the two cities is theta. And I actually put that right in your notes. So forget about the 360, you're getting distracted by it. Theta is both the angle between the stick and the sun, and it's the angle between the two cities. It is both at the same time. They are the same angle. That's all that matters. Anyways, to finish the job, we plug in 10 degrees for theta and 1,000 for D. So let's go ahead and do that.
Did you put imaginary numbers there to get a model?
No, what do you mean? That doesn't make any sense, Preston. That what your statement was, which just makes no sense whatsoever. There are no imaginary numbers here. I don't know where you would get that from. The answer is the circumference of the circle is 360 degrees divided by 10 degrees times 1,000 kilometers. Now that's a you job for you guys to punch into your calculator.
36,000
units.
kilometers.
Yeah.
So none of these are legitimate models that you have.
Well, it's a hypothetical problem of a hypothetical planet.
Definitely a problem, though. All of yours are none that you have.
All of mine are none that you have. I don't understand what that
Unless
means.
they're from the textbook. Are those the answers that you've gotten from a glossary in your textbook or whatever you read?
This is the correct answer to the problem. I have, yes, to answer, there is an answer key somewhere. I haven't looked at it in 10 years, but I don't need it because I know how to do this problem. This is the sort of problem I had to do when I was an astronomy student. I know this setup very well. It's classic. The stuff that you're learning here is classic. It's been studied for literally thousands of years. And this is the method of Eratosthenes. It's supposed to be cool, guys. The point of it is there was a person who lived on a spherical Earth, and with just a little bit of geometry, a little bit of knowledge of astronomy, and 2 sticks. Okay, and maybe he paid his friend a bag of shekels or something to walk the distance between the 2 cities, but he was able to measure how big his planet was without traveling around the planet. That is a cool thing. That's remarkably sophisticated, And it shows the power of geometry and what you can do. The real point is that the Greeks were sophisticated and knew many things about the world that they lived in. That concludes question 49. Boom. Okay, those were the two tough ones. The next three problems are going to be relatively straightforward in comparison. May I erase, or are people still writing? All right, I'm erasing.
I just need like a few more minutes just on the you can
Nope.
erase
Nope.
both diagram. Okay, cool.
William, I'll sip a sip of coffee. You take your time. Let me know when you're done, William. Give me a shout.
How did it this whoever he paid measured the distance between the two cities?
Supposedly, according to legend, his friend paced out and walked the distance between these two cities, which was similar to this. It was like traveling across the US on foot, or maybe traveling from like Rhode Island to Ohio or something.
No, I get that, but like, you know, from point A to point B, there are multiple ways of getting there. Like you can go up, down, left, right, whatever. But like instead of like, did he do a straight line?
He would have had to, or he would have had to account for his deviations, right? So Matteo, one of the things is we know about this from reading about ancient textbooks, and this is how it supposedly went. In fact, Matteo, the story gets more interesting the more you look into it. In Eratosthenes' day, in 100 BC, humans did not use units of kilometers to measure distances between two cities. They used a unit called stadia, a Greek stadia. And you see them writing about this and referencing stadia all over the place. But at some point, because history was long and knowledge had been lost throughout the Middle Ages, we lost the conversion factor from stadia to more modern units like miles or kilometers. So we know how many stadia that Eratosthenes calculated, but we don't know how correct he was in his answer because we don't have a conversion factor. So here's what the historians did. The historians argued that perhaps a stadia was similar to the length of a Greek stadium. And they took a survey of the length of all the ancient Greek stadiums that they could find, and they took the average, and they came up with a conversion factor to kilometers. And if you presume that's correct, which we have no way of really knowing, then we think he got the right answer to within 5% of the true answer. And
because I looked up the circumference of the Earth, and it's
42,000 kilometers.
Yeah, so I was like, okay, that's kind of close.
But remember, this is a hypothetical planet called Nerth. I think they didn't want to have you reproduce the exact, I think they should have just had you recalculate the exact same thing that Eratosthenes did. But they were trying to be cute about it, and they were trying to like,
Nerth.
Imagine you're on a new planet, but really the point of it isn't about Nerth. It's about reproducing the badassery that Eratosthenes did, right? And I encourage you guys, the fact that you're even talking to me so much about it means that you are curious and interested, and you can either, the textbook is one place, but even just go ahead and
is the zenith always 90 or no?
The zenith is always 90 with respect to the horizon.
No figure. So is it always 90 or no?
90 degrees.
Right.
What is it?
Degrees. 90 degrees or not?
From the horizon? You may not realize it, Preston, but your question doesn't make 100% sense to me unless you say, is the zenith 90 degrees with respect to the horizon? I would say yes. But if you say, is the zenith 90 degrees with respect to the sun? I would say no, not always.
You're not a constant. You're fake.
I'm fake? Like I'm not a real human?
No, like the numbers are imaginary. Never mind that.
In this case, the numbers are imaginary, yes. But they're similar to the ones that Eratosthenes measured. For instance, I happen to know historically that the records have that Eratosthenes measured 7 degrees between the sun and the zenith. And that's why these fake numbers are kind of close to what Eratosthenes did. Anyways, let's move in.
Question. I finished writing everything except when you said theta minus 90 degrees minus 80 degrees equals 10 degrees. The words after that, does that say between the zenith and the sun?
Correct. And I used BTW for between. Sorry about that.
Oh, no problem.
I know
That
for the
translates to by
LOL
the
kid,
way.
Mateo.
BTW is by the way, but yeah, you can
Okay.
use it as
In old short. All right. So Mateo, this is where
We're all group texting.
you and I have different eras from.
No, I'm just kidding. I'm just kidding. I was just making a
Oh, you're
joke.
making a joke. Yeah.
Yeah.
If you're doing like emoji chats, that's by the way. But in old shorthand, between would be BTW.
It's just in regard to a question. Can we type that, or does there need to be an equator?
My idea for what you would put in your homework is you would draw the diagram, everything we did here. I'd like to see this. I want to see that. I want to see this. Basically, everything I have on the board should be on yours. And I recommend drawing it out by hand rather than typing it, because when you're typing it, it might be hard to reproduce some of this stuff. Unless you're very, very good with diagrams and with, inserting equations and stuff. As
You
I've
still
said,
have all of those printouts for everybody, right?
the homeworks do not involve a printout. They involve you writing this on a piece of paper and turning it in. And I can show you examples if that's helpful to you.
On your printouts that you have for everybody?
The labs have printouts. The homeworks do not, because they're based on questions from the end of chapters in the textbook. So if you look over here under homework, just so that we can.
Is there a legend to that? One key is all we need, just so we can go over and check answers.
This is the answer key. I created it with you.
For our own general purpose. Was that not accessible though?
Yeah, that's you mean.
Okay, never mind it.
I'm sorry. Are you saying like the book's answer key? I don't have the book's answer key. This is our answer. Okay, you have to trust me that I know what I'm doing. I know that's tough sometimes. All right, I'm erasing and we're moving on to 52.
Not that, it's just as far as answering the question.
Answering what question?
No, never mind it. I meant as far as doing the homework legend.
Why don't we move on
and getting the answers to those, so that, like I'd said, with our own time, if we had to answer such questions.
Yeah, I'd imagine that you would
like alone, right? So that we can go over and check our answers, so that you don't just go and do it yourself and record it and then like do the whole like back and forth thing. And then for labs, have it be different. That's where the answer key would come in.
the thing
I would think.
The thing that I just wrote on the board is the answer key. That is the answer.
Where is it?
I just erased it, but it's going to be recorded in the video and you should be writing it down as you go. That's what you're supposed to do. Yeah, William's got it right there. Daniel, what's your question?
I was just wondering if I could read the question for
Yes, please.
number 52. All right, so the title is Eris Orbit.
All right.
Okay, the dwarf planet Eris orbits the sun every 557 years. What is its average distance, open parentheses, semi-major axis, close parentheses, from the sun? How does its average distance compare to that of Pluto?
Okay. It's going to turn out, and you're going to have to wait for Monday's lecture for the full description, that the average distance between a planet and a sun is also known as the semi-major axis of the ellipse. And this is going to be something that takes a little bit of discussion to flesh out. So save yourself there. But in all the three problems that follow, we're going to be focusing on the fact that planets orbit the sun not on circular orbits, but on ellipses. And I'm going to exaggerate, but this is a sort of a model of what an ellipse looks like. It's kind of a squishy circle. It's got a distance closest to the sun. We call that the perihelion. It's got a distance farthest from the sun. We call that the aphelion. And it has an orbital period, some length of time that it takes to go around the sun. And in this case, this is the sidereal period of the planet. There's also an average distance between the planet and the sun, which loosey-goosey you can think of as the average between the perihelion and the aphelion. It's some kind of average distance. We also call it the semi-major axis of the ellipse. This problem is solved using a formula called Kepler's third law. Kepler's third law is a legendary classic formula in astronomy that relates the period of the planet to the average distance. Now, the letter that we're going to use to represent the period of the planet is P, and the letter that we're going to use to represent the average distance or the semi-major axis is A. And this comes after Johannes Kepler's treatise in Harmonious Mundi. He constructed a relationship, Kepler's third law, that says P squared is equal to A cubed. Now, the units of this formula are very particular, okay? The units of the planetary period must be in units of years. The distance, the average distance between the planet and the sun must be in units of astronomical units. And if you do this, this formula works perfectly. Now, you guys haven't tried this yet, but I'm going to show you how to do squares and cubes and things. Let's start off by answering the question, find the average distance, and then we'll compare it to Pluto afterwards.
Oh, I'm sorry, what's the units for the A cube? I can't see that very well.
Not A cubed, but the units of A are astronomical units. But don't say A cubed. The units
Okay.
A are astronomical units. All right. In this case, we have the period, but we want A, the average distance. So we're going to start off by flipping the equation, and we're going to start by writing A cubed is equal to P squared, right? And that's pretty straightforward. Equations are symmetrical forward and backwards. To solve for A, we're going to get rid of the cube. Did anyone here take an algebra class and know how to kill off a cubed power?
Yeah.
Take
How
the
do you-
cube root.
Cube
You
root.
take the cube root, yeah.
So we take the cube root of both sides to get A is equal to the cube root of P squared.
Or
And now
P to the 2/3.
P to
Oh, I'm sorry.
the cube root of P squared. Be very careful with your notation here. Now I'm going to substitute in 557 years. And I'm going to get the cube root of 557 years squared. Sorry. Let me show you guys how to do this stuff. Get a pencil here. Okay. On your Casio calculator, there's a couple of buttons we want to sort of introduce and pay attention to. The key x squared is right there on your Casio. And at some point, we may need the square root, which is above it in orange. On the other hand, these two buttons here and here, this is your backspace and this is your negative key. Above the backspace in orange, might be kind of hard to see on my video. Above the backspace is an x to the power of 3. That's your cube power. Above this key here is the cube root key. And the fact that they're orange means we have to hit shift first. So let's start by squaring 557 together. Everyone ready to punch? Okay, type 557. And then we're just going to hit pow. We're going to hit square. Is that what you all see in your calculator? Now we're going to activate the cube root first by hitting shift. Boop. And then we're going to hit the plus minus key to activate cube root. How many sig figs should we keep?
3.
That's right, 3 in, 3 out. So what should we round our final answer to?
67.7
Good. And the units?
AU.
That's right. It's very good, Matteo. This is a magic formula. You input years and you get out AU. So our final answer is 67.7 AU. Very good at paying attention to that. Box that, because that's one of our answers. Now, the only other thing we have to do for this problem, it's a very simple problem, is to just compare our answer to the semi-major axis of Pluto, to the average distance to Pluto. I'm going to erase a little bit up here and write down this, compare to Pluto. Now, I happen to have memorized, but you could have looked it up in the back of the book in the table of planetary data, that the semi-major axis for Pluto's orbit, which I am writing A subscript Pluto, is 39.5 AU. And you might have remembered me saying something like Pluto is about 40 AU from the sun. Okay, compare means take the ratio. That's how we do things in this class. When we compare, we take the ratio. So I'm going to divide the semi-major axis of Eris by the semi-major axis of Pluto. And then I'm going to get 67.7 AU divided by 39.5 AU. And what do you get?
1.71
And we'll just round it to
AU or whatever. I don't know.
No, not AU. AUs cancel out. And I'm going to round back my sig figs to 2 sig figs.
No.
Matteo, I ask you again, think about it carefully. What does the 1.7 mean?
The ratio between, or like the difference between. The,
Not different. Difference means subtraction. It is not the difference.
Okay,
So if the ratio is 1. William.
Sorry, I have to start getting ready for work, but I'll watch the recording after to finish.
I'm sorry, William, the last 2 problems are real quick, but I understand, but I promise you, sorry if things got drawn out a bit here.
No problem at all. And it's not like it's due, like I have until Sunday, obviously.
Yep.
So
Yep.
gonna be awesome.
Oh my
See you.
gosh, I didn't realize how late it was getting. You know, the questions in the discussion are good, but anyways, let me explain. 1.7 is a ratio. It means roughly 2 times further away than Pluto. That's the number of times bigger this distance is than that distance. So it means roughly 2 times farther from the sun than Pluto. And that's our final answer. Okay, number 53 and number 54 are also based on using this equation. That's why it's going to go quickly here. But let's proceed with great haste. May I erase? I'm doing it.
Yep.
Okay, John, Cole, anyone? John, you want to read a problem for me?
Yeah, that's fine.
All right, so chapter 353.
Sorry. New planet orbit. A newly discovered planet orbits a distant star with the same mass as the sun and an average distance of 112 million kilometers. Its orbital eccentricity is 0.3. Find the planet's orbital period and its nearest and farthest orbital distance from the star.
Okay, we have 2 things to do here. Find the orbital period, and then we want to find the perihelion, that's the closest approach, and we want to find the aphelion. So we have 2 problems. We can call it, I don't know, problem A and problem B if you want. They didn't do that, but we could do that. Okay, first order of business. They gave us the average distance, but John noticed that the average distance is in kilometers. Matteo couldn't help but remember that A should have what units to use P squared equals A cubed?
Astronomical units.
Sorry?
AU. It should
That's-
be the
That's right. And that means that we need to convert kilometers to AU. One of the things I like to do is to pick random people and have them practice dimensional analysis. John, you're up for special torture, okay? Sorry, buddy. You can do this. This is part of this is walking you through this and forcing you to do it. John, do you have, so let me just once again explain what you're doing here, John. You have your average distance in kilometers, but this formula needs astronomical units to work. So what we're about to do is we're about to convert from kilometers to AU. And to do that, we're going to need our 4 steps of dimensional analysis. Can you open up your book, your notebook to the first or second day where we did the 4 steps of dimensional analysis? It was in that recorded video that you were supposed to watch. Do you have that in your notes? Cole's got it, so if you can't find it, Cole will help us, but there should have been a big box and it should say the 4 steps. John, do you have that?
I don't think I mean, I can't find it right. If someone else has it, then by all means.
I know 1 AU equals 150 times 10 to the 6.
10 to the 6
Kilometers.
what? Kilometers.
Kilometers.
So yes,
Yeah.
we are going to need that. That's your conversion factor. And we will need that conversion factor to do this. But John, we need the 4 steps of dimensional analysis. And you can find them in that video that. So John, if you didn't watch that video, then you got to do that. That's like a big deal, okay? If you guys look here, lecture 01, I think it's in this one here. And I'll go over to it. Is this like a YouTube within a YouTube? This is getting abstract here.
I have it written down in my notebook.
Okay.
If you need me to reference it, I can.
I sure do. We need help here. Because remember, one of the tricky things about this is that I already know my 4 steps of dimensional analysis. So it doesn't do me any good to do this problem. It does you good. And these are the 4 steps you're supposed to have written down. This was the exact moment, 43 minutes and 29 seconds into the lecture, I had us write down the 4 steps of dimensional analysis. Now, who's that person talking in the background there?
That was me.
Who's
Nina.
me?
Nina.
Nina. Okay. Hi, Nina. Nina, you read them to John, but I don't want to let John off so easy. I want John to do this. What's the first step?
Write down the number to convert with units.
So John, if I were to pick on you, I'm using Nina as a helper here. What should I write down to start off?
Write down the units you said.
The number to convert with units. I need a number with units. You're writing down the thing you're trying to convert. What am I trying to convert?
The I don't know. I'm really lost. I'm not gonna lie to you.
Okay, well, that's fine, but we have to try to realize we're lost and then to push through that lostness. That's part of the process. But Nina, do you know what we're trying to convert? Let me try it this way. Does anyone fucking know what we're trying to convert?
Yeah. So, can I
Yeah.
say it, or
Sorry?
should I say it, or should we wait?
Yeah,
For...
no, say it. Do it. Let's do it.
Okay, so it's 112 times 10 to the 6 kilometer.
That's what we're trying to pause right there. That's
Okay.
what we're trying to convert, John. That's how we start, by writing down the damn thing that we're trying to convert. And we're trying to convert this to AU for our formula to work. Okay, what's the second step?
Then times. So AU goes on the top, and then
Whoa.
kilometer.
Whoa, just slow your roll here.
Okay.
Because this is hard for people, I want to break it down into manageable steps. The second step is you multiply by a division bar. Full stop. Now we can go on to the third step. What's the third step? I want to be systematic about this.
You're gonna do your units first and then plug in your numbers.
Right. So let's do units next. That's step 3. Someone, anyone, just shout it out.
Kilometers on the bottom, AU
Yep.
on top.
And AU on the top. That's step 3. And step 4 is we put the numbers in using conversion factors. And you'll see that step 4 at the bottom. 4, put numbers in second using conversion factors. John, you need to go back and get this into your notes. Critical, buddy. Okay. Okay, so where do I put my numbers? I've got 1 AU is 150 million kilometers. What goes where? Anyone?
You put 1 on top and then 150 times 10 to the 6 on the bottom.
Good. Okay, now we can punch it into our calculators. Please use the EXP key. All right. I'm going to do it with you. We're going to divide this divided by that because it's on the bottom. So 112 EXP6 divided by 150 EXP6, 0.75 AU. I'm rounding to 2 sig figs because why not? Remind yourself that this is A. We just converted it. Now we can find the orbital period. The period is the square root of A cubed, which is the square root of 0.75 AU cubed. This time we're going in the opposite direction. So we're going to be using our cube key here in orange, and then we're going to square root after it. So let's start with 0.75. Our first job is to cube it. So I'm going to go and follow along with me. Shift, this button here is cube. So shift, hit your backspace key. Now we're going to square root, which is in orange. So we hit shift, square root. What's my final answer?
0.65.
And the units?
Kilometers?
No. This is a magical formula. AU goes in for the distance.
Oh.
But what comes out?
Years.
Years. That's going to take some getting used to. Okay. The second
It'll just
part-
take me a moment.
Sure.
My phone died, so I just reconnected.
Okay, Ethan, let me know when you're done and I'll assume that's good.
Yep, I'm all caught up.
All right. We're not done with this problem because we have to find perihelion and aphelion, but that's really simple. I'm going to erase this part. All right. To calculate perihelion and aphelion, there are simple formulas. Perihelion is A, the average distance, times 1 minus the eccentricity. And we can find the aphelion semi-major axis times 1 plus the eccentricity. Let's plug in our values. We know the eccentricity is 0.3. By the way, the eccentricity is the percent squishiness of the orbit. Because planets orbit on ellipses, they're squishy circles. And that tells you how squished the oval is. Okay, so the perihelion distance is A, 0.75 AU times 1 minus 0.3. To do this, we're going to make use of parenthesis keys. The aphelion, if you want to write that down too, is 0.75 AU times 1 plus 0.3. All right, let's start with the perihelion. Parenthesis keys are located here and here. We've used them before. I'm going to clear it out, all clear. I'm going to do 0.75 times open parentheses 1 minus 0.3. When I close parentheses, that does the 1 minus 0.3. Then I have to hit equals to finish the job. My cat's freaking out. That's our final answer. Round it to 2 sig figs, and what do you got?
0.53.
And the units?
AU.
That's right. That's how close the planet will get to the sun. Now you guys do the same thing again. Use your parenthesis keys 1 plus 0.3. What do you get then?
0.98 AU.
Very good. And that's the farthest distance. Box it up. That does, and by the way, the last problem is exactly the same as this one. So we're going to use those same formulas all over again. 3 problems that are actually very simple once you get the hang of these 3 little formulas. Matteo, since you were just unmuted for a second, why don't you just read us 54 and we'll be done with this. Hold on, wait. I'm going to erase. Anyone got a problem with that? All right. Matteo, chapter 354.
Halley orbit or Haley orbit?
Yeah, this is a comet, a famous comet called Halley's Comet, or
Okay.
Halley's Comet.
Halley's Comet orbits the sun every 76 years, and it has an orbital eccentricity of 0.97.
Hey, I just want to point out, I'd like to point out that it was 76.0 years, wasn't it?
Yes.
Precision matters. Okay, keep going.
A, find its average distance from the sun.
They also gave us another given. What was the other given besides the period? Sorry.
Oh, and it has an orbital eccentricity of 0.97.
Okay.
Excuse me?
Yeah.
Where can we find this exact equation?
It's not an equation, it's a problem. We're reading a problem, right? So do you mean where do we find this problem? Or do you mean where do we find?
Whatever you want it to mean, you can make it mean. Where can we find it?
But you're not being obvious as to what is it. I don't know. Like, do you mean equation or do you mean, you said equation, but what equation are you referring to? Are you referring to Kepler's third law? Are you referring to?
Whatever your problem is.
Okay, if you meant where is the problem is in the handout that
like you have had this the entire lecture so far, Brendan. I don't get what your deal is.
I don't get what your deal is, Preston. You don't make any sense to me sometimes, to be perfectly honest. You ask me questions that are really confusing and I'm on your
But if I ask you what the equation is, it's probably the same as a problem. I don't have any pertainment to your personal issues, you know?
I don't have personal issues, pal. I just know the difference between an equation and a problem, and I'm not sure that you do. That's where the fucking confusion is. The confusion
You
is—
don't have to get explicit with me. All I'm saying is I just need to know or want to know where we can find the equation or the problem. Where we can find the problem, if that makes it easier for you.
That makes it much easier for me. So what we do is we go to homework. We go to homework 3. You right click chapter 3 PDF, and we're reading from here. We're currently on problem, not equation, but problem 54. And those terms matter to me because I can't follow you if you're not.
How do we solve the problem?
Well,
by not computing anything through an equation, Professor.
we are going to use an equation to solve the problem, but we have to read the problem first. That's what we're doing.
All right, I suppose. If
So,
that makes sense.
Mateo, now that we have our givens, what does the question ask us to do? Please.
Okay. A, find its average distance from the sun. And then in parentheses, it says semi-major axis.
Right. And this
And B, find its perihelion and aphelion distances.
okay. They're telling us to find the average distance, which is the same as the semi-major axis. There are two different ways of saying the same thing. Average distance between the planet and the sun is also known as the semi-major axis, and that is letter
Is
A.
that an equation?
Because
that's different from the one you had where it's supposed to equal the cubed root of p
No.
squared.
Well, I'm about to get there. This is not an equation. This is terminology. Now I am going to use the equation. The equation, one of the equations we're going to use, the one for this problem, is Kepler's third law. And Kepler's third law is p squared equals a cubed. That is an equation. This is not an equation. That's a terminology. That's a definition. A is the semi-major axis, is the
That's an
average.
equation.
That's not an equation. I know there's an equals there, but it's just shorthand.
You're wrong again.
Okay, look,
By problem or by equation, whatever you want to call it, you're wrong.
well, you know what? If you think you can do a better job, feel free to teach the
To
course.
run a YouTube channel?
Yeah, that's right.
Okay, I'm only asking one simple question. I just wanted to know where we can find the equation. You don't have to give me an issue.
You can find the equation here on my board, in the textbook, in the PowerPoints,
Thank you.
anywhere on planet Earth. All right. First, we're going to find the average distance. We have the period in years. We proceed exactly like we did before. A cubed is equal to p squared. We're going to take the cube root of both sides. A is the cube root of p squared. And now we plug in the 76.0 years in for p. All right. Let's see if you guys can remember how to do that without my help this time. The trick is, can you punch this in using your calculator? And if you can, I'd like to hear an answer.
17.9 AU.
Very good. Let's see how he did that. So we start with 76.0 years. We're going to square it first. That's this key, square. Boop. Now we're going to cube root, which is shift and then the plus minus key. 17.9 AU. Box it, that's the answer to A. Question B is to find the perihelion and the aphelion distances. For those two distances, we use the second set of equations that we used in the previous problem. Perihelion equals A times 1 minus E, and aphelion is A times 1 plus E. Our eccentricity has been specified. We've calculated A in the previous part of the problem. So now we substitute in 17.9 AU times 1 minus 0.97. And the second part, 17.9 AU times 1 plus 0.97. Why don't you guys punch that up? Let's see if you can get it without my help this time. Use the parentheses keys. Those are important.
So the first one would be 0.537.
That sounds about right. Let's see how we did that. So we have 17.9 times open P 1 minus 0.97. We close parentheses and then we hit equals. 0.54 is what I would have rounded it to, Daniel. 2 sig figs.
Okay.
And what are the units?
Let's see.
AU.
There you go.
Thank you. I was blanking out for a bit.
The eccentricity does not have any units. AU transfers right to the answer. Let's do the second one now. Second verse, same as the first. 17.9 times open P 1 plus 0.97 close parentheses equals. Daniel, what do I want to round it to?
Okay, I can't. All right, I can't see
Well,
from that. So
Do
the
it on
decimal.
the goal is for you to do it on your calculator.
Right. Okay, let's. Okay.
But fair enough. I don't have a good, if I activate the focus thing, it's going to screw up my whole lecture. Thankfully.
All right. Okay, so 35.3.
That would be 3 significant figures. The eccentricity has 2, so we're going to round it back to 2 sig figs.
Okay, so then 35.
35.
AU?
Is that it? We're done?
Thank God. Yes, we're
Yeah,
done.
okay.
All right. This concludes homework number 3. Preston, you and I are going to have to figure out how to talk to each other in a way where we can understand each other, because I am trying to help you guys here. I'm trying to
Don't think about it too much.
Probably good advice. Fine. In any case, homework 3 is done. Please submit them hopefully before Sunday. And next week we do heliocentric stuff and we're going to study Newton's laws. There's going to be more math coming, so hang on to your hats. I'll see you guys on next Monday. Okay.
Thank you.
Yep. Peace out.
Thank you. Have a good night.
See ya.
Good weekend.
Wait.
Oh,
You mind if I
stay
take a picture
warm.
of that last thing?
Yep. Sure. Let me get you here. Right there.
Yep.
All right.
Thank you. That's all I need. I much appreciate it.
You got it. Anytime. Bye, guys.
All right. Stay safe and stay warm.
All right. I will. I'll try.